So, welcome everybody to the second day of the SaaS conference, and we have the second invited talk by Daniel Kastner. And Daniel is a CTO of Absinthe and also one of the founders of the company. He has been working a lot, an awful lot, I would say, on safety security, software security, sorry, and safety in particular. And he's on the working groups of the ISO 26262 and IEC 61508. I never remembered the numbers correctly. And besides those international standards, also is in the MISRA C and another MISRA board about software quality metrics. And these are not international standards, but are, in a sense, de facto standards for the software industry in their fields. Okay, today he will talk about apps interpretation in industry, and that's it.
All right. Thank you for the introduction, and welcome to my talk. Well, as already said, I'm Daniel Kastner from the company Absinthe. And first of all, I'd like to thank the PC, the organizers, for the invitation to give this presentation here. So it's really a pleasure and an honor for me to be here. Well, today I'll be telling a bit about our experiences when commercializing two different abstract interpretation-based analyzers from two different domains, and talk a bit about, well, the insights we had in this process, which to some degree were a bit surprising, but well, we'll see. Okay, so these, of course, a lot of people were involved in what I'm going to present here. So all the people at Absinthe, for example, and also many people from ENS and Sorbonne. So here I did the slides together with Reinhard Wilhelm and Christian Ferdinand, who are also founders of Absinthe. Maybe I'll just give a brief introduction of the company first. So Absinthe, well, we are a spin-off company from the university in Saarbrücken in Saarland, from the group of Reinhard Wilhelm in programming languages and compiler construction. The company now is 26 years old, so we are around for a while. And the focus of the company really is to develop verification tools for embedded systems with a focus on functional safety. And also, in the latest years, also cybersecurity properties. So it's verification tasks to make sure that these systems work all right and don't harm people. And our customers come from all different industry domains which are related somehow to safety or security requirements. We have about 50 employees at the moment. And this is, well, the list of the products we have. So you can see, okay, well, abstract interpretation comes up quite a lot. So the first tool here is an abstract interpretation-based tools for worst-case execution time analysis. The second one is also abstract interpretation-based analyzer to look at the maximal stack usage, to compute worst-case stack usage of a task. Then the third one is SPLASH'23, so well, that's a source code analysis on C and these days also C++, again based on abstract interpretation. Then we also have some other tools, mostly in the timing domain, which are not purely abstract interpretation based, but where there are some components also based on abstract interpretation. And then we also have the ComCert compiler, which of course is a formally verified C compiler, where basically the formal method is theorem proving. And today I'll talk a bit about the first one, so AIT, the worst case execution time analysis, and also about SPLASH'23. So essentially I'm going to tell two stories which are a bit different. So, well, the focus is in both cases is so it's not the same. So in the first, I'm going to focus on the process of insight, of gaining the insight to develop the analysis and how we modeled this. So it's essentially a worst-case execution time analysis, which was not around before. So we had to figure out what the requirements really were and how to model it in a reasonable way, so that it also is usable in practice. So here I'm focusing on a bit on in particular on the variants of abstract interpretation we are using there, the different applications. and to some peculiarities in there. And I'm also talking about some illusions we had where we were quite a bit optimistic at the beginning, and also when we just had pure luck, which is also important. Okay, and essentially the message is that, well, in the end it turned out that it works, and it could only work because we were using formal methods, because, well, we try to really prove properties of programs here, but it's really important to choose the right formal method and apply it in the right way. And then another aspect is, well, what's the cost? What does it mean to develop something which then really will end up in industry and is non-trivial? Okay, so before really going into the topic, well, worst-case execution time analysis obviously is relevant for real-time systems. So in a real-time system, the correctness just not only depends on the logical correctness, but also on the correct timing behavior. So you have real-time task, and if a real-time task misses its deadline, then that's bad. So either it's really a failure which can cause really people to come to harm. So imagine a flight control computer which doesn't react in time, or the steering in a car. In other cases, it's not as severe, but still annoying because it degrades availability. So if you have some assistance system in a car which bails out all the time, then, well, you're not going to be happy with it. And you can also come to harm because of that. And of course, this is something which is known in the safety standards which are around. So this is the view of the ISO 26262. You have a clear requirement. Yes, well, you have to know the an upper estimation of the resources you use, which first means execution time, but then also storage space. So obviously, you should not run into Stack Overflow. That's requirements you find there. And with respect to timing, so there are two different levels where you can reason about time. The first one is the worst-case execution time. So this is really the execution time of a bunch of instructions which form a task, and you want to know how long it takes to execute that on a given hardware without considering interruptions and so on. And at the next level, that's the worst-case response time. Here you are bringing in preemption time when this task is interrupted by another task or gets blocked waiting for some utexes. So if you add all this together, then you have the worst-case response time, so basically the end-to-end time in the system. And here you also have to do some kind of scheduling or schedulability analysis. But the basic ingredient is the worst-case execution time, and that's what we are looking to. All right, so so that means the worst-case execution time problem is, you have some execution platform, a processor, and a program, and then you want to know how long it takes. So this sounds a lot like the halting problem, but I already put the upper bound there. So of course, computing the exact worst-case execution time is not possible. But computing an upper bound is quite simple, so you could have a constant time algorithm which always says infinite. That's perfectly all right, but will not make people very happy. So, of course, the goal is to have an upper bound of the worst-case execution time which is close to the true behavior. And, that's difficult because it depends on the execution state. So one aspect, of course, is the path inside the program. So the history of the program, so that means that inside the program you have the combinatorial problem of the different paths. And in addition, you will have the hardware states. So you have to distinguish whether you have a cache hit or a cache miss and so on. And this ends up in a huge state space. All right, so the tool architecture we developed over the years is shown here, and I'm going to tell the story a bit along the line of this chart. So the analysis starts at the executable, so machine code, fully linked executable. We first decoded computer call and control flow graph. Then there's a couple of static analysis on it. Then we come to an control flow graph with the results of this annotated here. We do an analysis of the microarchitecture, and then to give the timing information, and then we compute the longest path. So far, so good. So when we started, there were some analyses already available, like interval analysis, abstract interpretation-based interval analysis. We just applied on the machine code level. And also here for path analysis, there was from Lee Malik implicit path enumeration. So essentially, the control flow graph was translated into an integer program, and then you had a maximization problem just to compute the longest path. So that was more or less the starting point. And of course, the most challenging thing or the most interesting part is this microarchitectural design. So here we try to capture what's happening inside a processor. So that means that we want to analyze the machine semantics, and for that we need to develop an abstraction of the machine semantics. So essentially, the goal is to track the state of the machine resources so we can reason about, well, what's happening inside the architecture. And a very important part of this is the cache analysis. So obviously the cache has a huge impact on execution time. So if you can't predict the cache, well, you don't even need to start. Okay, and well, that was the original starting point. So there were the so-called timing schemata, which is basically a structural induction over the program, where, well, it's very straightforward. So if you have, for example, the conditional statement, then you take the time to evaluate the condition and then compute the maximum of these two paths. Well, if you have an instruction sequence, you sum up the execution time of the instructions. Well, for a load, for example, you then determine the execution time of the load. You already see that the implicit assumption here that the execution times were constant. So at the time you had processors like Motorola 68K. It was the case. Each instruction had a fixed execution time, so the problem was rather simple. But then people started using caches, and then of course the execution time of an instruction is not constant anymore. And first work here in this area was, for example, from Frank Müller and Sang-Yul Min. So here there was a cache analysis for direct map caches, which was the first attempt to look into this, and Sang-Yul did an extension of timing schemes to look at caches. And well, the problem was that this was typically limited or not generalized for set associative or fully associative caches. So there was no solution around to deal with this. And that was the starting point of our work. So it was essentially the research work of Christian Ferdinand. And well, the goal was that we want to classify memory accesses in the program as well, always a cache hit or always a cache miss. And the idea would be was that, well, it should be possible to support the cache architectures which were around. So like fully associative caches where all blocks can go into the same line, or set associative caches where you had a set of blocks into which the cache memory blocks were sorted. And well, then it turned out that there is a very efficient abstract domain to represent the cache, and the idea is basically to look at the to compute an abstraction of the execution state at the end of an instruction trace. And well, that means that we map memory blocks to some cache block and associate it also with its age inside the given cache line. So the cache eviction strategies least recently used, for example, work like that the oldest element of the cache is evicted. So having this concept of age in the cache is quite important. Okay, so that was the central idea, and it's a very efficient representation. Well, I'm going to come to this in a minute. A second aspect which was important, so the focus of the original analysis was to have a must analysis, so that we can guarantee whether a block is in the cache. We had a complement that it's essentially a may analysis, so if you know that the block may not be in the cache, you know it can't be in the cache. That was the second aspect, and the third aspect is the persistence. So, you can define a memory block to be persistent if, if all accesses to this block will be in the cache after it has been accessed once. Then you know that it will not trigger any cache misses later on, and then you can bound the number of cache loads in a program segment. Okay, so so we had this the must analysis, the may analysis, and also some concept of persistence. But still, when applying it for the first time, the overestimations were quite big. And when looking into this, it turns out that the cache in that case, later it's a property with also other architecture components have. They tend to take some time to stabilize. So let's just look at the standard fixed point iteration. So we will come, so let's say this is the program flow, then you hit a loop, and then of course in the first iteration of the loop, the memory accesses will be cache miss. Right, and then you go in the next iteration of the loop, and then when you compute the join in the must analysis, well, you join with it's not in the cache, so nothing is in the cache. And then you execute each iteration of the loop under the assumption that you only have cache misses, which of course is absolutely not what happens. And so the idea, with hindsight, it's pretty obvious, but the idea is then, to do some concept of virtual unrolling. So basically you peel off the first iterations of the loop and then only do the union afterwards. And then, of course, you can distinguish the iterations where the cache is being reloaded or loaded from the iterations where it's stable. And so that was also an important point. Okay, so that was basically the starting point. So this was essentially the dissertation of Christian. It was in '97, and then, we thought, okay, that the problem is solved, and so let's try to. So there's really something new. Let's try to build a company and sell it. So that was in '98. And it turns out that it was not really the case. So the first point where reality hit was that it works very nice with least recently used caches, but they were rarely used in industry because they are kind of expensive to implement. So people are using like pseudo LRU strategy, for example, where it's a bit more difficult. And then, it's not the cache alone which has to be taken into account, but quite a bit more. Okay, so it turns out that there was still some work to do, and that was the starting point of a research project called the Daedalus, together with Airbus, where Patrick Couzeau was the coordinator, and that was really an opportunity to find out the points which were still missing. All right, so the first idea was, okay, we had a cache analysis with a must and a may analysis, so where we could predict the cache behavior alone pretty well. And so the prerequisite for coming up to this is that, we were quite familiar with this formal methods background, worked with abstract interpretation a lot, so that was really the idea. Which enabled this. Okay, and then, if you look at some, at the processor architectures which are around, then you will find out that there is a lot of speculative hardware features. The caches are not the only ones. You have a pipelined architecture where you have different stages in the pipeline the instruction proceed through. Position inside the pipeline can be reordered. There are out-of-order execution pipelines. There are things like branch prediction, prefetching, and some more aspects. And, you have the caches, but you also have prefetch buffers and so on. And so all of this plays together. And the effect is, that the execution time really depends a lot of, what has happened before. And it's not just the cache. So here there's a bit of an illustration. So let's just take these 3 machine instructions on something like the 68K. Instruction execution time was constant. So best case was the same as worst case. Then there were, let's say, some flash accesses which were buffered. So here you could have already a difference between the best case and the worst case for these 3 instructions here. And on something, well, realistic at around the year 2000, the difference or just for these 3 instructions could be a factor of more than 100, depending on whether it has been in the cache and what else has happened before. So essentially, these speculative hardware features can cause timing accidents. Like if you hit the cache, well, then if you access a memory block, then the accident is that it will not be in the cache. And, well, that causes a penalty. So that's one way to talk about it. And these kinds of timing accidents could be cache misses, stalls in the pipelines, branch mispredictions, or just collisions on the bus. Then if you have DRAM memory refreshes, misses in a translation look-aside buffer, and so on. All right, and well, what this abstract interpretation model can do basically very efficiently is to analyze the execution history to a certain program point. And well, the idea is to be able to prove that certain timing accidents will never happen. So if you know then then well you do not have to take into account the penalty for the timing penalty for such a timing accident to happen. So you try to prove that certain bad states cannot happen. Okay. And so that's now the methodological view. So here in this block, there is some abstract interpretation-based analysis, so a value analysis where we traditionally compute the values for registers, memory cells, and so on, a loop-bound analysis, and from this we try to determine infeasible paths, so that, of course, they don't have to be considered. And then the core is this abstract interpretation-based analysis of the microarchitectural state centered around the cache analysis. And well, the worst-case path, so this gives the timing information, and then again, worst-case path can be computed by integer programming. All right, and then the next step would be really to look at the pipeline, because all the other stuff, the speculative mechanisms are somehow integrated in the pipeline. So that was some other dissertation from another founder of Absint, Stefan Thesing. So here, well, it was an abstract interpretation-based modeling of the pipeline. And well, it essentially was a power set domain. So this is something which was quite expensive. But it did work. And well, the platforms, the processors we were looking at in the Daedalus project was Motorola Coldfire and PowerPC 755. So, and here there were also the less predictable cache replacement strategies, which also had to be modeled. And we also found a modeling for this, but the precision was a bit reduced. Okay, so so basically this pipeline analysis then really bound the different aspects together and made it possible to also model the other predictive speculative features. So we had the first paper where we presented the entire approach was at an MSoft conference in 2001, which then 20 years later got the Test of Time award. So as a quite influential paper, so it really opened a lot of subsequent research. So also from, let's say, the university in Saarbrücken, there was a kind of research which originated from this was to classify caches and come up with general classification also of architectures, to which degree they are timing predictable. That was Jan Reinecke. It essentially originated from this as well. Okay, so in the pipeline analysis, so the power set domain is necessary because you cannot easily prune states which you can consider irrelevant. So for example, you do not, so if in a pseudo least recently used cache strategy, like you have with PowerPC, you can assume that the empty cache is the worst case state, right? So the worst case cache state for some instruction sequence is some pre-filled cache, which depends on what instructions you are trying to execute. So you cannot just assume that the empty cache is the worst case. And neither you can assume that a cache miss is the worst case. So it can be that, for example, if you have a pipeline and you have a condition, well, if you have a cache miss at a program point before, it takes some time, the pipeline is stalled, and when you evaluate the arguments, you know which branch you will take. And if you had a cache hit, then you would have run into the condition very fast. Operands might not have been available. You could have speculated into the wrong path, which triggered a cascade of further cache misses. So that means you cannot really decide what you can throw away, and that makes it expensive. And then we tried also to look into model checking. So that was Stefan Wilhelm. He tried to do a model checking variant of the pipeline analysis. But there was a trouble that it was very hard to connect the abstract interpretation and the model checking. And it also, from a perspective of efficiency, was not really better. Okay, so we did not follow this model checking approach further. A slightly different view is that, well, we tried to analyze different difficult architectures, so we also developed a pipeline which could be analyzed very well and suggested it to the hardware community. And, well, nobody used it, so that was a pity, but it would have made life quite easy. Well, it's not entirely correct, so the Calray architecture is designed with a very predictable pipeline. So that would be an example of where it was heard. Okay, so that means that so for the precision, really the caches, the pipelines, and so on have to be analyzed together. Trouble is that there is no compact cache domain if you try a model checking approach, and vice versa. In the if you look at the pipeline, well then you can't really do a lot better than a power set domain in abstract interpretation. Okay, so and well, at this stage, with the optimizations we did in the data loss project, in the end we really could come up with a working analysis of the cold fire processor with a 15% overestimation, which was very good and better than what Airbus has used before with the safety margins they applied, and also likewise on the PowerPC 755. So that was then very nice, and then we thought, okay, that's it. Now we really have analyzed two microprocessors which were widely in use and could make Airbus happy, so they were using this also. And we thought, okay, now we can get rich. We just sell this everywhere, and that's it. But unfortunately, that was not really the case because, well, there is really a reservation against using formal methods. So it's something many people don't understand, and using something people don't understand, there is a very big resistance against that. You see it in Europe, but even more in the US. So that's kind of a trouble. And I'm going to talk also about this in a minute a bit more. And then there is a huge amount of different hardware configurations. So there are lots of processors. Processors can be configured in different ways. So in the end, it's not something you have what everybody uses. So as of today, I think we have more than 25 different target architectures we support in the timing analysis with a lot of different compilers. So that means that for a new processor, this has to be instantiated, which takes a lot of effort. Okay, so that's basically how it looks like. So the commercial side of it, you can see it here. So we start from the executable. You can specify tasks or interrupt service routines. We compute the worst case execution time per task or interrupt service routine with visualization, the information of the critical path. And then there are lots of tool couplings, for example, with SCADE and other model-biased design tools, with scheduling tools, and also, let's say, with Jenkins, so people can easily integrate it and automate it. All right, and another important aspect is, let's say, the confidence. So people have to trust the results, and yes, with abstract interpretation you can prove that the model is correct, but the question is still whether you have the right model. So that's essentially so philosophically viewed, this is a question of the logic versus epistemic doubt. So the logic doubt is solved by this, but the epistemic doubt, what about the environment? Do you really capture the real system which is running? That's something else. And it turned out that we had to spend a lot of effort in order to deal with this. So yes, the soundness proof is one aspect, but then what about the implementation? So you have to have some confidence that the implementation is all right. So what we used here is basically we could generate the implementations of the analyzer from a specification. So that was the program analyzer generator pack at the time. And then we have to validate our models. So, binding that together, there are validation suites we can run where we can really check that the implementation of the tool corresponds to what we think it should do. And it was also necessary to, let's say, document our development processes and say, okay, we meet the requirements you have for safety critical systems. And to validate the model, well, the trivial way is for execution time analysis. You run a task, and then the execution time you observe must be bigger than the worst case execution time bound we compute. But that's not a very deep view. So you could have underestimations which are just shadowed by overestimations in other places. So you can't really rely on that. So what we now do is to do an in-depth validation. So basically, the analysis essentially predicts all execution paths with all hardware states, which we think can happen. And then these hardware states will correspond to observable events, and then all these events must be predicted by the model. So this slide is pretty lengthy. So essentially, we look at performance monitoring features like log ticks, cache misses, mispredicted branches, at bus traces and instruction traces, from which we collect all these informations. And we instrument the model to emit the, let's say, abstract traces for these different types. So we come up with a prediction graph, and then any real observable sequence of events then must be contained in this prediction graph in exactly the same order. And then we can say, okay, now we have reasonably validated the model. And so typically we start from the hardware manual of the processor, and well, often you have, or not often, but it can happen that you have silicon bugs and the architecture doesn't correspond to the model or to the manual, or the manual just was wrong. And of course, we can't model the manual. We have to model the processor. So, and we also learned that it's a different thing. All right, so I mentioned some research projects, and that, well, all this was quite costly, and we were quite happy that we managed to get research projects where we could fund all these developments. And the cooperation with Airbus was also very good. So because we had a customer which was really interested and supported us, pointed always out where some problems were in a cooperative way. Okay, then we could basically generalize the approach, so the same tool architecture can be used for stack analysis as well. And then I have the slide, but I'm not going into any kind of detail here. There are multi-core processes around where you have interferences between the core, where the state space really explodes, and then you cannot have a static guarantee anymore. So in that case, it's just, let's say, the path analysis which remains, and the value analysis, loop-bound analysis, and so on. But for these kind of multi-core processes, you have to combine it with traces. But that also is based on the same tool architecture. So what we did for this worst case execution time analysis for predictable processes could also be used in other areas. So to sum this up, so I've talked a lot now about how we came to this. So it was basically kind of a new research area, how we came to the solution. So we had some ingredients we started with and did the rest. And let's say the effort to come really to the first working prototype was about 15 to 20 years, person years. And we started with a very good background in formal methods to do this. And so now this is massively more. There is a lot more effort which is which went into this. This was just the initial start. So if you want to really try something out in practice, you should plan for some time. But then it can also be applied to other cases. Now I'd like to tell a slightly different story. So here now it's about AS3, and here we had a cooperation with the ENS. So basically, when AS3 had a working prototype, they Xavier and Jerome, so the group of Patrick, considered usable. We basically started cooperating there to do the commercialization of the tool. So I guess a similar story than what I just told with AS3, you can have from Xavier and Jerome and Antoine if he's here. So, and this basically now starts after this. So if there is already a viable prototype around, which works pretty well, what else do you need to do to make the customers happy? So in case of the timing analysis, it was a bit interwoven, and here there is a bit, it's more clearly separated. So what I'm now going to tell about is, well, what we did since starting with the original state to, let's say, to meet the requirements or the expectations of the customers, where we had to extend the analyzer, and what about automation and scalability. And here, let's say, here the message is, well, if you want to have it out in practice, of course, the analysis has to be precise. It must be automated as much as possible, and it must be easy to use. Yes, and it also turned out that safety norms are a very important motivator for all of this, also with the timing analysis. And this is also something I'm going to talk a bit more about. Okay, so the development of AS3 started around 2000 in the group of Patrick and Raja Couzeau at ENS. So some of the original authors are sitting in the audience here right now. And 2009, let's say, we went to Paris for half a year and started to learn a bit about AS3, and then started a commercial development of it, but still with a very good cooperation with the guys from ENS. And the initial state we did was, this was a chart I basically stole from a presentation of Antoine in 2010. Well, at that time, AS3, it stands for Analyseur Statique de Logiciel Toriel Embarqué. It looks for the absence of runtime errors on a subset of C. It's semantic-based sound, and well, if you have a synchronous real-time system, you can analyze it as without any false alarms. So that's already very nice. So that essentially was the starting point. Well, it was a command line tool. So you could invoke the analyzer, could indicate which abstract domains you wanted to activate, supplied a C program, got the result as a text file, which was fine. And there was also a first, let's say, rudimentary graphical user interface, so that was more or less the start. And then I grouped what we did in the years afterwards in different categories and tried to collect a bit where we spent some effort. And one big part was usability. And of course, to some degree, it's trivial. So you have people who can't operate a command shell. So yes, you have to have a user interface, a graphical user interface, but it goes deeper than that. Because runtime errors at the C language level means undefined, unspecified behaviors. So it's where you have a lack or let's say trouble with the language definition. So that's difficult areas of the programming language. And then you have an analyzer which can have false alarms. The analyzer, what it does internally is also very complex. So you have a complex thing which reasons about other complex things, and if you want users, people to understand this, you have to spend quite some effort. Okay, well, then rather mechanically, the preprocessing was separate before, so you had to run the preprocessor alone. So some people are not able to do this, so we integrated the preprocessor into SPLASH'23, generalized it to more platforms. And then there are also, like similar to AIT, a lot of couplings to other development tools. So if you do model-based development, it's nice if you can just push a button and get a result, and ideally also get the findings connected to your model elements. This was rather interesting. So there are some SPLASH'23 directives you can influence. So basically you can communicate with the analyzer to, let's say, locally increase the precision of the analysis. So you can parameterize the abstract domains essentially. And so by default you just wrote it in the code. But then there are people where the code was frozen, so it was impossible to change the code anymore. And of course, with model-based code generation, you don't have the source code at all. You have a model from which the code is generated, so you cannot put anything in the code. So we developed basically a mechanism to specify this stuff outside of the code itself, and that was really also a prerequisite for some domains to be applicable at all. Well, then you have some findings, and often, well, you just want to say, okay, it's a false alarm or it's justified. I have to think about how to repair it. That was also something. And then the build process can be very complex. So we tried also to simplify this, for example, by importing it from a JSON compilation database, so that you don't have to collect all the include parse macro definitions, which can be quite some work in a complex project. Okay, then formal requirements, like with AIT, you have to demonstrate that the tool works all right. So there has to be a qualification support kit to show that, in addition to the proofs, the soundness proofs, that it really works all right. Yeah, we also had to extend the content. So from the first sequential semantics, one did an extension to concurrent, to an interleaving semantics, so which really broadened the capabilities of the analyzer a lot. So it was possible to talk about data races, deadlocks, other concurrency issues, and could also completely model the API of some operating system norms like OSEC, AUTOSAR, RINC. I'm going to show this in a bit more detail later as well. Then in particular for cybersecurity, you often have, let's say, properties where you want to check where information flows to. So that can be handled by a taint analysis. So we incorporated basically a general taint analysis into SPLASH'23 that you can say, okay, if I have a sense of corruption here or somebody tampers with my inputs, which parts of the program could be affected in a user configurable way. Code guideline checking, like MISRA, C, well, that's not rocket science, but it's something people have to do. And in a framework like SPLASH'23, it's easy to do, and it would be silly not to do it. But it's also a lot of work. And then the data and control flow analysis is a verification topic of its own, so we also had specific support for that. And then another small detail is now that people can work reasonably well with C. They decided, oh, well, why not move to C++, which opens up another completely new can of worms. Okay, then there is some application-specific stuff like peculiarities of some code generators. We also have some, let's say, vulnerabilities we are targeting out of the box. We had to work a lot about tuning the precision to reduce the false alarm rate further, for example, by a state machine domain, interpolation domain, and some other abstract domains we brought into the analyzer later. And essentially, a very big part of work was also to really get it run on large-scale software, because even in embedded systems, the software size is becoming huge. Okay, so that would be, well, let's say the commercial view of it. I mentioned it all, so that's basically the summary. And to show how it works now in practice, I'm going to quote from a presentation I had this year at the SAE conference, where basically we looked at how SPLASH'23 is run on integration analysis of automotive software, so in entire control units with a multi-threaded analysis. what let's say the results are on these kinds of code and how they look at all. Okay, so I've mentioned the interleaving semantics for talking about concurrent threads of execution. So the foundation is an abstract interpretation-based interleaving analysis. And if you want to talk about these concurrent issues, originally they were not in the C language. So you had to have primitives telling the analyzer when these things happen, like when a process or a thread is created, when you lock or release a mutex, when you disable or enable all interrupts. So you have primitives in ASTRE which communicate these, let's say, operating system events to the analyzer. Okay, and then if you have a concrete operating system, well, then you can build an abstract library. So you have an API, for example, in AutoSAR. If you want to lock a mutex, it's get resource. So you can implement it with these kinds of primitives and also do some bookkeeping. So you can report alarms like lock without unlock or double lock, that you can also find some defects in the modeling. And for users, it means that they can just run the analysis on such an OS without any change. And then in AutoSAR, you do not create the processes explicitly. You have an operating system generator, which generates, let's say, tables for the tasks automatically. So this is not part of the C code. So if you want to do this automatically, it's necessary to understand this XML specification, which is absolutely unreadable, can be megabytes just text. And so we implement essentially a converter where we extract the relevant information from there. And that means what tasks we have. So in this automotive world, the tasks are then grouped on applications. The applications are assigned to cores. Process control is done by alarms and events. Of course, task priorities have to be known, whether the tasks are preemptible. Then you have to know about the mutex locks or the spin locks, and so on. So this is automatically extracted. And that means if you have such an AutoSAR system, essentially you can run the analysis out of the box. And then I've mentioned that it's possible to interact with the precision of the analyzer. So essentially this, Xavier did a lot of work on this. That's essentially by partitioning execution traces. So there are different aspects, value partitioning or control partitioning. We also generalize it to state machines. So you can also partition state machine states. And also with loop unrolling, you can say, okay, you partition different loop iterations. And these, there are also primitives to control this. For example, there is one primitive where you say, okay, this is the state variable of some state machine, and then an ASTRE does an automatic partitioning according to the automaton states. And it's quite helpful to use this because you can tune the precision of the analysis then to really concrete software project. Okay. And this is how it looks. So we just took 10 automotive projects. That's integration projects. And of course, we can't tell anything about what they were doing or from which vendor they came. And you see that the code range, so nothing is below 1 million lines of code. So it's, I think it starts at 3, goes to 40 here in this table. And the biggest project we saw was 100 million lines of code, where we count the pre-processed lines of code. So the software size is pretty gigantic. And so you can see here the time for the analysis typically ranges around a day, sometimes a bit more, sometimes a bit less. And memory consumption really is manageable for this kind of software. And in terms of runtime errors, let's say, so sometimes ASTRE can say, okay, there is a definite runtime error when you're sure that in a given execution context you will run into a runtime error. And here, that's some breakdown. So you have an average of 14 or 15 alarms per million lines of pre-processed code. So with a bit less certainty, general alarms about runtime errors. So here there are around 733 per million lines of code. So you can see that the precision is, so that's still quite a number of alarms, but given the software size, it's reasonable. And data races, so here we can see, okay, objects we could prove to be free of races range between, let's say, 70 and 99%. Average is 85. This is quite high, but for the number collection, we did not distinguish. Well, we for example, we treated an array as an entire as one object, and of course, Astrid can distinguish cells in this array elements and say, okay, on this particular cell there is a data race and on others not. So here we are, let's say, we are making it look a bit worse. So not. You don't have 15% on all the objects in data races on all the objects in automotive code. Okay, and now this is the contribution from this precision tuning. So here, and of course, it's not possible to spend infinite amount of work in doing this. So you could see here that's the number of directions we inserted. So here it was just about 50. I think here there were about 1,000 of these directives. And then we tracked what the benefit of it was, how we really could improve the analyzer or the results by this. So here we said, okay, how much we could reduce the number of runtime error alarms, data race alarms, and what the change in time and memory consumption was. And that was a bit surprising at first because, well, when tuning, so typically you increase the precision of the analyzer by these directives. So the expectation would have been that, well, it makes the analysis more expensive. But in the end, on most cases, it's actually not true. By making the analyzer more precise, you reduce analysis time and also memory consumption. Because essentially what happens is that you strip away spurious contexts you should not have tried to follow at all. And by cutting away those, you make the analyzer more efficient. So that's so on average, we could reduce the number of alarms by 20%, number of races by 8%. Well, but still sometimes, so I think I can't read it here, but somewhere so in this example, for example, analysis time increased quite a lot and also memory consumption, so it can also happen. Okay, so that's how it looks on realistic projects. So just to give a feedback on how complex these kinds of applications are. And now let's say to look at the market. Well, if you talk to customers, then well, from a verification community, so or a program analysis community, we think this is an important thing, but actually people are not excited about this. So it's well, to put it carefully, not exciting or perceived as a burden, or you could also say a pain in the ass. And people really don't like this a lot, and they are also often not considering it very important. So it's more work. If you come along with a formal method, it's something new, people don't really understand. And another psychological aspect is, well, if you start doing something like this, you admit that what you did before was not perfect, and it could be seen as your fault. So that also is some aspect. So what it means is that, well, it's not really a selling point. You don't sell a Mercedes and says, okay, my brakes crash less often than with Volkswagen, although it might be correct, but that's not how, let's say, all this stuff is sold under the assumption that it works. And then you can't say, well, for me it works more often than for you. Yes, then also a level of expertise is a problem. So, well, people have to have some understanding to operate these kinds of tools. And, well, so what is an accepted benefit is, well, if you fix bugs which are escalated. If you had people chasing a data race for weeks with the entire team, they are very happy to buy an analyzer and don't ask about the cost, but otherwise it's difficult. Automation is important. If it helps people reduce the effort to, well, if they have to do something and they can save time by using a tool, then it's also good because then in the end you're saving money. And this is where we come to the safety norms. They are important because they essentially define what it means to develop a software with due diligence. So it's what you really should do if you write a software which could kill or harm people, what you should do. And if you have a requirement that you have to do this somehow, then that's a big step. And then it basically becomes an insurance. They have to tick a box, oh, I have to look at the control flow, so let's do control flow analysis. And that kind of gets rid of, oh, why should I do this at all? And okay, so that's why these safety norms are important. Avionics, so this is the view of the DO178C, which is very nice. So that's a nicely written standard, although it's not, if you read it, it's not very accessible. So it means, well, it says, well, with testing, you cannot show the absence of errors. That's already quite an insight. It defines software verification process. It says, yeah, well, you can use formal methods if you like. It lists abstract interpretation along with theorem proving and model checking as formal verification methods, which you can use. Mostly the standards say the standard verification technique is testing, and if you want to use something else, people are not happy, you have to do additional justification why you do it. Okay, so that's the formal method supplement. So you can see all these kinds of errors I've talked about are deemed critical, so you have to deal with them, and you can use formal methods to reason about them. So that's the aerospace view. Now let's have a look at automotive. Oh, this got collapsed by the standard slide, by the aspect ratio. It's quite interesting. So here you have so that's the method you can use for software unit verification, so there are formal verification, and then you find control flow analysis, data flow analysis, static code analysis, and static analysis based on abstract interpretation with as different methods with different levels of recommendations. And if you look at the definition of abstract interpretation, so it's a collective term for extended static analysis, which introduces analysis such as extending the compiler parse tree by adding semantic information, which can be checked against violation of defined rules, and so on. So, well, I would say the definition is not really optimal, and so there is still, let's say, some leeway to improve these standards. And if you look at the railway norm, actually there are two of them. Well, they talk about formal methods, but they don't know about abstract interpretation. It's not even listed. So that means that, let's say, that there is kind of a gap between the scientific community and what you see in these standards, and it's really important to interact with the standard people and make sure that, let's say, if there are some verification techniques which can be used, well, people should know about it, and it should somehow end up in these standards, because, well, from, let's say, from an academic perspective, if you develop something, if it's not in the standards, then it's already an argument against not using it in practice. So I would encourage everybody who has some spare time to try and join these committees and explain people about, let's say, the verification methodology you are doing and why it could be good to do it. Okay, general outlook. So software becomes really more and more complex. It really explodes. Cybersecurity becomes more and more important because all the classical safety systems are opening up. And are communicating with one another, then, well, all this AI stuff, the neural networks, machine learning, is kind of disruptive. And that's also interesting because people are using them all over and then are saying, okay, there's the traditional safety arguments don't work here anymore. So, but we can't do it without, so let's just do it with them. And then why should we do all the stuff for the rest? So basically, the traditional formal verification methods you could apply on deterministic systems are becoming questioned. So that's really bad. And then also you have increasingly dynamic behavior like programming language like C++, or you start to see people running in POSIX or Linux environments, or even more service-oriented architectures. That's the new automotive software architecture. Yes, and then of course the safety of the, let's say, neural networks, machine learning, it's an open question of its own. Okay, so then I'm more or less in time. So let me conclude. So I try to give an overview of, let's say, what we did in the past years. So we tried to, let's say, commercialize formal method-based tools for industrial use. I summed up some of our experiences. So, of course, so if you look at abstract interpretations, these kinds of analyzers really have a benefit. They can prove things people could not prove before. But, well, bringing this to market is really some significant, takes some significant cost. So you should calculate some years before you start earning some money with it. It's essential to let's say to bring users to use the tools actually. So that's also something not to be underestimated. And again, the role of these safety or cybersecurity norms is essential because really people tend to do what's written there, and if it's not written there, you have you're in trouble. All right, then. Thank you for your attention. And in case of any questions.
So there are questions, even on the Discord.
Mm-hmm.
Hey, so great talk. I've done some more static analysis in industry, and one of the things that I've always found difficult was iterating with the people using my tools. Mm-hmm. In particular, I developed a tool that would find slow spots in Android applications, and it found tens of thousands of places where the safety property was violated. Mm-hmm. But the process of like iterating with the developers who were using my tool took long enough that they eventually didn't continue using that tool. So what I was curious about is how do you keep the people that you're working with continually engaged as you refine the safety properties and tailor it to the kinds of properties that they care about the most?
Yes. So this is something we really try to understand what the safety properties are. People are really interested in and see how they can be addressed from inside the tool and whether we can improve it. So maybe one example was, let's say, the data and control flow analysis. So in the DO standard now talks a lot about data and control coupling. So essentially so this goes beyond the usual code coverage metrics. You try to measure somehow how different software components can interact with one another, and whether you, in the testing you did, you exerted all component interactions you could have. So it's not just about, let's say, having coverage of the code, but also coverage from different components. And so this is something which, of course, we can support with ASTRE. So if people want to do about the data and control coupling, they have to know at first what at all they can have. And with ASTRE, we could compute an overestimation of this data and control coupling. And well, essentially what it meant is that we had to introduce this concept of software components. So it's not about just the pure language anymore. So you can specify now what you consider a component, bunch of function or files or whatever, and then you try to compute the dependencies between these components. And then you have some insight about the data and control coupling, what you could possibly have as an overestimation, and then with that information you can look at your testing. So that was a classical example where people asked, I have to do this verification property, but the tool does something similar, but it's not really what I need, and then we try to support that better.
Thank you.
Other questions?
Hey, thanks for the talk. You showed this nice table with how many sort of potential bugs you found. Mm-hmm. Do you have any idea of how many of those were actually bugs and how many of them were false alarms?
No, not really. So, I mean, the software size is absolutely huge, and of course there are some obvious things. So yes, we did find out-of-bound array accesses or dangling pointers, which were more or less trivial to identify as true findings. But then it really becomes difficult. So what we also have in this, let's say, concurrent analysis, that we can separate between different execution stages. So, for example, you could have just initialization tasks running, and when they have finished, then the normal working tasks start of them is synchronized, so you can have different phases of execution. You can also model with ASTRE. And now let's say you look at the data race, you see there are 2 or 3 processes involved, and ASTRE reports a data race. But it is a true defect, could be that there is some mechanism to make sure that one of them, that they can't really overlap at all, or that you have some, let's say, some timing properties in the system which would avoid a collision from happening at the same time. So is this a real defect then or not? So really finding out can be quite some effort. And also with the examples I've shown, we got the code, so we could look at it, but it's really big piece of code. And from the vendors themselves, we don't have information. They don't tell us we have found this and that, true bugs, the rest was irrelevant. They don't tell us. But it's a good question, yes.
Yeah, so I have a question about, in IIT, you have a lot of analysis which depend on the history for the cache and pipeline analysis. And I was wondering, because in real-time systems, often you use a preemptive scheduling. So how does this affect the fact that you can compute history-based analysis when the history can be flushed at any time?
Yeah. So the standard AIT analysis basically assumes that there are no interruption from the outside. So it just focuses on an uninterrupted execution of the task. Then if you have, let's say, preemptions, then you have to look at them in the scheduling analysis. So the scheduling analysis would compute critical instance, how many interruptions you could have in the worst case. And then another contribution of the static analysis is that you could calculate some cache-related preemption delay. So if what the worst case preemption costs would be that this and that amount of cache lines would be evicted. So you have some concept of worst case preemptions costs you could have. And if you know you can be preempted at worst 4 times, then you can apply this additional cost in the scheduling analysis. But this would be something which is not part of the analysis itself. So you have the scheduling analysis around the response time analysis and would add this as an overhead. So that's something where you have support, let's say, from inside the tool and also other stuff like, let's say, if you have DRAM refreshes, you can more or less calculate some general overhead and also add it to that.
So we are a bit late on the schedule. Last question.
Thank you. Thanks a lot for a very rich talk. I have a question concerning the certification of cybersecurity properties, which seems to be a bit of a different game because it's more open-ended in the sense that I think you first have to specify what is your threat model actually. And then it's also still very process-oriented as far as I understand, that you have to go and be able to convince someone that you've followed the right steps when you implement your protection mechanisms, which is perhaps also where static analysis can help, but I don't know if you have any thoughts about this.
Well, so it's also on a theoretical level. Cybersecurity is more difficult because you tend to have hyper properties, and in safety you have rather normal, so trace properties, normal properties. But of course, it's for cybersecurity is more difficult. Because it's not really clear. So there can be side channel attacks, and you just have to. So there are some vulnerabilities. That's the easy part. It's clear that some things constitute vulnerabilities. You can find those, and you can also try to assess the effect of certain side channel attacks, like the Spectre or vulnerabilities that's rooted in there. But whether that's enough or not, so I don't think you can really say, okay, you have proved to be safe from cybersecurity attacks. You can just say, I've excluded this vulnerability and this particular scenario, I can prove it will not happen. Under the assumptions I could make so far.
So thank you very much. We'll thank you, Daniel, again.
Yes.
And we start with the next talk. Now I have to find the name. Sorry. Daniel Schopp will talk about on-demand analysis, and you can start.
Great. Thanks for the intro. Thanks, everyone, for coming to my talk. My name's Daniel. Oh, yeah, there's the slides. So I'm going to be talking about on-demand call graph construction. This is work that David Sekatz worked on during his internship at Prime Video, and also the rest of my colleagues in the same team contributed as well. So let's motivate the problem. So it starts from the observation that a lot of interesting static analysis problems require us to reason interprocedurally. So as a motivating example, let's look at the problem of SQL injection. So let's look at this program here where we're creating a SQL query here based on some input. And let's ignore for the moment that you shouldn't be concatenating strings to create SQL queries, but for the sake of this example, please bear with me. So if we want to reason about this problem, we want to figure out whether the name variable there may be user-controlled, untrusted input. So in other words, this is a taint tracking problem where this prompt function here can be considered as a taint source, and the connection.query function there can be considered a taint sink. Now, in order to figure out what actually flows into this taint sink, we need to reason about where this anonymous function that's being returned from getQuery actually is invoked. So that's pretty, in other words, we need to construct a call graph. There are some easy cases where you just call a function by its name, like calling getQuery at the end of the program here. But in many modern languages, you have higher order features as well. So the function getQuery actually returns another function that gets bound to a variable and then called. And then these call edges that involve higher order functions are a bit trickier to detect. But that's still pretty straightforward if you just have a bunch of code that still fits on one slide. More realistically, though, these two places in the code might actually be very far removed. There might even be millions of lines of code in between. And then at that point, it becomes pretty hard to actually build a call graph for the whole program, because you need to reason about all the stuff that happens in between there as well. And now at this point, you basically, the most standard approaches, they build a whole program call graph where you are faced with a trade-off. Either you can try to be precise and not get too many spurious call edges, but then that can be pretty slow depending on the exact abstractions that you're using. Or you can use a faster approach that then is more imprecise and may create a lot of spurious edges in the middle there that aren't really corresponding to real program executions. So that trade-off is a bit unfortunate, and ideally what we would want to do is to really only care about these relevant edges that somehow involve either taint sinks or taint sources or both, and not about all this irrelevant code in the middle that isn't relevant for a particular goal that we're trying to prove. So what we really want to do is reason just about the necessary call edges in a demand-driven way, rather than having to analyze always the entire program. So that sounds like a pretty simple and straightforward idea, but it's actually not so easy to do that in practice. And the main reason for that is that if you have higher-order functions, you're essentially connecting your data flow with your control flow. Depending on what you do with the function that you use as a value, if you store it on the heap, you retrieve it again from the heap somewhere else, you now need to reason about kind of your data flow and your control flow at the same time in sort of a mutually recursive way. And in particular, also, this work is motivated by the fact that a lot of the state-of-the-art work, including on on-demand analyses, still assume an upfront whole program call graph. So for example, there was this very nice work at PLDI 2 years ago that took an arbitrary abstract domain and showed how to turn it into an incremental analysis, except that you still needed this upfront call graph. So what we're trying to do here is help close this gap and allow us to build sort of a fully on-demand analysis that can then hopefully scale better to large programs. So to summarize the contributions I'm going to talk about, we start from the scenario where we have some client analysis and we have our on-demand call graph algorithm. The client analysis will then ask some questions to our algorithm, like what are the callers of function f, what are the callees on line 7, things like that. And our analysis is parametric on an underlying points to analysis that we then use to answer these queries. And the points to analysis that we rely on can itself assume a call graph, and I'm going to show how we can essentially bootstrap a call graph from nothing in order to answer these queries, and then get back to client analysis with some answers. Then we, on the theory side, we formalized an abstract version of our algorithm, and we defined what it means to be on-demand sound in the context of call graphs, and then taking that together, we proved that our approach actually is sound, and we verified that with Isabel Hall. On the practical side, we implemented the approach for a small subset of JavaScript using synchronized pushdown systems as an example of like a modern points to analysis framework. And we evaluated that approach against essentially running the same approach on the entire program versus just on small subsets, on just individual call sites or functions. So to show you how the approach works at a high level, let's consider again sort of a modified version of the initial example, where, and let's say that we want to figure out what are the possible call targets on line 11 there. And we're going to do this by interleaving two types of queries. We are going to ask some underlying points to analysis, what are the values some expression E can have on a particular line, in particular what function values can it have. And also we're going to sometimes ask what are the callers of a given function across the whole program, some given function f. So when we want to figure out what are the possible callees on line 11, for example, we would start by issuing a backwards query asking what value can the variable f here have on line 11. And then the first thing that the analysis will do is realize that, oh, so okay, we go backwards from there, and then we reach the beginning of this run and say hello function. At that point, we realize f is a parameter, so really to figure out what value it might actually have, we need to figure out where run and say hello is being called. So we would issue a forwards query saying, where is this function being invoked? In this case, it's very straightforward. We just see direct static syntactic reference to it, and we can figure that out just like through lexically looking at the program. And then we add, but in principle, this could also be more complicated, like run and say hello might itself be used in a higher order way and being passed around and so on. So then we add an edge to a call graph saying, okay, line 17, there's a call to line 10 that's relevant for answering our initial query on line 11. At that point, the initial query trying to resolve f can make progress because now we know where run and say hello is being invoked. So in particular, we now see that this query argument passed to the call on line 17 is going to be going to determine the value of f. So then we keep going backwards on that query, trying to figure out what does the variable query contain. So then we see that it's being returned by this getQuery function, and in principle, that could also be a higher order call. So first we have to also resolve what is getQuery actually calling. In this case, it's again a simple statically resolvable call. So we add another edge for that, and then finally we then get to the actual getQuery function body, and here we see that we return a value from there that then flows into query, and then that flows into f. So at that point we're essentially done and can add the call edge that we actually care about to the call graph. So the call on line 11 to the function, to the anonymous function return on line 2. And in principle, if there were other references to run and say hello in the rest of the program, we would have to keep going until we find all the possible arguments that are being passed to that. But in this case, this is the only reference there. So we're done and can say, okay, that's the relevant bit of the call graph that we needed to construct in order to answer the call targets on line 11. And I want to emphasize here again that so we're parametric in how we answer these blue and orange arrow queries there. Under some assumptions that I'll get to later. All right, so that's the basic overview of the approach. Now the question that some of you might have, and that we certainly had when we came up with this, since we're sort of using all these queries that need information from each other, can it be the case that there are cycles between queries? So could we have, for example, some cycle of 3 queries that we need to answer in order to make progress on each one of them? So the question is, when does this happen? Can this happen? To which the answer is yes, this definitely can happen. So here's a fairly minimal example. So let's say that in this example, we want to now find the callers of function f. And then we could start from individual syntactic references to f in the program and see where they flow and where they might be invoked. So for example, we could start in the body of g because f is being referenced there, like statically. So at that point, we see that we get to the end of function g, and we need to figure out whether this e parameter is eventually going to call its argument or not. So we need to ask what is this e value actually? What is this e variable actually going to contain? At that point, we reach the beginning of function g and say, okay, then in order to figure that out, we need to ask what are the actual call sites of g? So again, we would start from where g is being referenced and see where then that might flow. So we would start here. At that point, we would have to we would again reach the end of function f, and at that point we would have to again figure out what are the actual callers of f. So we're exactly in this cycle where we would sort of first get an answer to a previous query to make progress on a later one. So what can we do with that? So the key intuition to solving that problem is that if we look at an actual execution trace, then the things don't happen in this sort of cyclical way. They happen in order of the actual data flow in the program. So for example, you would first pass G to F, and then that in turn would enable calling G from line 3. That would in turn enable calling G from line 6, and that would in turn enable calling F from line 6, for example. So there's always some previous data flow starting from some reference to a function that then gets passed around and then gets invoked before a call actually happens. And the key thing that I want to emphasize here is that these, like in a real execution, calls to different functions and these data flows of function values are interleaved. So, and we were before trying to sort of answer one query at a time. So that's kind of a mismatch. And the intuition to our solution here is, well, since the function calls are interleaved and there's all this sort of like interleaved stuff going on, why don't we interleave the queries as well? Which is to say, like, let's try to answer them concurrently. So saying, if we have like query 1 and query 2, then we run query 1 for a bit. Whenever that makes progress, we can inform query 2 that we found another call edge that's related to query 2, allowing that to make a bit more progress. That in turn may enable progress of query 1 again, and so on, until the whole thing reaches a fixed point. So that's the overall intuition. That still seems a little bit ad hoc, and like, does that really work? I don't know, seems a bit dodgy, doesn't it? So in order to make sure that we didn't miss anything there, we wanted to prove a soundness theorem about relevant bits of the real call graph. And I say relevant bits here because we need to recall that we're doing an on-demand analysis. We don't want to have to over-approximate the entire call graph. We just care about a little bit of it. And our soundness, and the way that we formalize what the real call graph is in order to not tie our approach to particular languages, a particular syntax, particular heap memory models, heaps, and so on. We just model the program as some function, the semantics of the program as a set of traces, where the events in the traces are things that are related to calls. So you can see that as essentially collecting semantics that only cares about what function calls happen and what references to functions are being passed around and things like that, without fixing the exact memory model on language features around heap and so on. So now the soundness theorem that we are then proving about this real call graph is the following. So if our call graph construction reached a fixed point, where this squiggly arrow here is essentially a non-deterministic sort of transition system that can perform one of the steps we've seen before. So we can add an edge to a call graph based on data flow that the points to analysis already found, or we can start new queries based on what we still need to answer. When there's no more step that can happen here, then we want a certain soundness statement to hold. And typically the way that you would end up in this situation is that you start from an empty call graph and some initial set of forward queries, fs0. So essentially you want to find out what are the callers of these particular functions, and a set of backwards queries, es0. So what are the values some particular call expressions can have at runtime. Those initial sets might come from the client analysis that wants to answer something like a taint analysis problem or something like that. Then you run the algorithm. You perform a bunch of these steps, possibly in sort of a non-deterministic order. You can run them concurrently. You can also run them in parallel. Then, as that happens, the set of queries, you might issue some extra queries in order to answer the original one. And then, after that process terminates, the call graph CG that you get out at the end that is going to over-approximate this intersection in the middle here. And this intersection in the middle is exactly the part of the call graph that we care about. Those are essentially all the calls that involve either a function for which we asked, where is this function being called, or it involves a call site for which we asked, what are the callees of this particular call site. So that's essentially the theorem that we've proved under the assumption that these points to analyses that answer individual queries are actually sound. And I'm going to tell you what that means in the next slide. And yeah, since this involves a lot of like tricky reasoning about sort of getting the fixed point correct, we formalized that in Isabel to make sure we didn't miss any corner cases. All right? Now let's talk a bit about these soundness assumptions on the underlying points to analysis. So the format, the interface that we expect from these, I'm going to go over the forwards example. The backwards one is kind of analogous. Is the following. So we assume that these points to analyses might need a call graph up front to make some progress, but this can be a partial call graph. And then you also give it a query. For example, you ask it, where's f being called? And then what we require of this analysis in order to consider it sound in terms of the assumption of the previous theorem is the following. When there's a real trace in a real execution of the program, where we give it a partial call graph that's compatible with some prefix of this trace segment relating to f. And then there is a real trace that ends up calling f from some other line as the next event in the trace. And what happened so far in the trace is compatible with the call graph that we gave to the forward points analysis. Then it must be able to discover this next event in its abstraction. However, it's representing trace sets, so you're typically going to have some finite abstract domain that would actually represent the actual sort of sets of traces here. So intuitively, that means that if you ask one of these on-demand points to analyses a question and you have some data flow from some reference to function f somewhere, and it passes it around, but the trace so far only involves call edges that you have already discovered, then you are expecting this points analysis to correctly track the data flow across these call edges that you already told it about via this partial call graph. So that's essentially the soundness criterion for the forward points analysis. There's a similar backwards one. And we think a nice part of this approach is that in using this modeling, we didn't at all have to think about what kind of data flows are there in the program, like what's the heap, where can you store functions, how can you pass them around. So that simplifies quite drastically the amount of sort of formal modeling we would have to do of the language in question. It's fairly general. All right. Let me quickly then go over the rest. And there's also some additional assumptions around reflection. Let me, before wrapping up, talk a little bit about the evaluation of this. So we implemented this for a pretty small subset of JavaScript, instantiating this SPDS framework, synchronized pushdown systems for that subset. We didn't do it for the whole language because it's a fairly complex framework, and handling modern JavaScript introduces all kinds of like pathologies you would have to deal with. So we focused really on sort of the higher order aspects of this. We then generated a synthetic data set that artificially creates a lot of like higher order function calls where you return functions, you pass them around, and so on. We use QuickCheck for that to have a nice way to sort of generate structured random data. And in the future, we leave extending this to like handle modern JavaScript code up to future work. The implementation is online. You can find the artifact link in the paper. It also contains the Isabelle theories if you want to take a look at the soundness statement and so on. Now let's talk about the results here. So we essentially wanted to answer, does this approach actually allow us to not have to think about the whole program, or do we end up in this kind of degenerate case where we need to still answer every query about every single call set in the program to answer some initial one? In order to figure that out, we started with a bunch of essentially sets of initial queries. The x-axis here essentially represents selecting n random call sites in the program and asking our approach to resolve it. And then on the y-axis, we see how many other queries did that require resolving. And we do see that this does indeed increase as we sort of ask for more call sites to be resolved initially. In terms of runtime, we first got a little bit of a surprising result here. So the black dots here are essentially our baseline where we upfront ask it to resolve everything in the program to kind of model a whole program call graph approach. And then the first surprising thing is that yes, on the left part of the graph here, we are sort of faster than computing these black dots, but for larger query sets, that is not always the case. So we were scratching our heads a bit and like, wait, why is that happening? But then we remember that this approach really relies on concurrency in order to be correct. So we also implemented it to use parallelism, multiple threads, and all that. So we were suspecting that might be the culprit. And indeed, when we then actually measured CPU time as well, we got a more expected result where answering more queries will actually take more CPU time. But if you ask for all of them up front, you get a lot more opportunities for speed up from parallelism. Otherwise, you might start answering one query, the other cores are sitting there doing nothing, you get a few more queries later on, then 2 more cores can maybe do something, and then you end up wasting a bunch of like wall clock time compared to if you just ask it about every call site from the start, then you always have enough analysis to do essentially. So that's the performance story there. So if you care about energy consumption or stuff like, yeah, for some reason CPU time is more important to you than wall clock time, this might still make sense. For instance, like in an interactive setting in IDE, you might not want to really use all the cores of your system constantly to answer this quicker. So summing up, I showed you an on-demand call graph construction approach that's parametric in an underlying points to analysis. So we can use existing state-of-the-art points to analyses like SPDS that assume a call graph, but we can then bootstrap a call graph kind of out of nothing without having to do any kind of upfront whole program analysis in the first place. We formalized it and proved it sound, and you can take a look at the artifacts online. That's it. Thanks for listening.
Well, I have a question. You use as a baseline your own tool running on all possible queries. Why didn't you consider choosing a all program construction tool?
Yeah, that's a good question. We debated whether or not we should do that. But essentially, at that point, we would be essentially comparing SPDS to like a different algorithm because there's no like whole program SPDS instantiation for JavaScript. So we wanted to really compare like the same points to analysis on demand versus the same points to analysis whole program. Otherwise, we might be measuring all kinds of things that are not really super relevant to whether this on-demand approach gives you any savings.
Okay, so there would have been too much noise. That's the reason. Okay.
Yeah.
Are questions? Oh.
Thanks for a very nice talk. So I was wondering if you're running the on-demand analysis, you couldn't use the concurrency as much. So could you do something to evaluate some parts on speculation? Maybe you can use ML for that, I don't know.
Oh yeah, that's a good point. Yeah, I think that would work. You could always just run a bunch of queries speculatively in the background, and then if later on they turn out to be needed, and the first query will sort of ask the system whether the query has already been answered or whether it should start it will already get the answers. So yeah, you risk doing a bit of extra, like unnecessary work, but you would get the same kind of, speed up as for a whole program setting, I guess.
Okay, other questions? So no, so let's thank again the speaker. Coffee break.
So I think we'll wait 1 more minute for people to come in, but if you like, you can already come on stage.
They told me they could only do 4/3 resolution, so
yes,
I had to
restructure.
But now I'm a bit disappointed. No, it's okay.
Oh, well, I also restructured my slides yesterday, and so some of them were a bit more cramped than they should be. Yeah, well.
Yeah, I remember the highlighting in red.
Yeah, exactly. Yeah. Yeah. And you're in the École Normale Supérieure? Yes.
No, I did École Normale Supérieure. What do you mean?
Are you in Jérôme's room?
Yes. Yeah, I'm his PhD student. Yes. So I did this with him. And I'm in the beginning of second year. That's ENS is in a group of universities. So we have to put the my subject of thesis is not about this. It's continuing what did Mark Chevalier. It's working about operating systems in SPLASH. We're proving things with SPLASH, but
okay.
So that's just something else.
Yeah. Okay. All right, so welcome everybody for the second session for today. And the first speaker in the program will be Jérôme Bouillot, who is working with Jérôme Ferré. And the talk is about symbolic transformation of expressions in modular arithmetic. The floor is yours.
Thank you very much. So let's talk. The work I will present to you is a joint work with Jérôme Ferré, and it's about symbolic transformation of expressions in modular arithmetic. So let's start with a bit of motivation. So there is critical code that has to be certified free of runtime errors. And abstract interpretation, as you saw this morning, allows proving properties, semantic properties, and in particular, prove the absence of runtime errors. Most of those semantics properties are represent linearity constraints, and in many programming languages, in particular C, there are explicit and implicit modulo computations that are nonlinear constraints. So the proposition is to rewrite expressions to simplify them. And because we get easier expressions, it's easier to identify patterns, and in particular, linear interpolations. So that was the motivating example. So I told you we had implicit modulos in C. Let's see an example. So we take the assumption that integers are stored on 32 bits. It remains general, that's just a parameter of the analysis, but it has to be fixed. So in this example, we have SI that is equal to -1, UI that is equal to 1, and we then compare SI to UI. And because SI is an unsigned integer, there is an integer conversion that is done, and SI will be converted to an unsigned integer. So there will be a wraparound, and SI will be interpreted as 2 to the power of 32 minus 1. So we now want to prove properties, mathematical properties on those programs. So we will represent them in a way such that we can do operations in Z, over Z. Okay? So we will introduce a new tool, a new syntax feature that is modulo over on an interval. So for every k that is an integer and L and U bounds, k modulo LU is just the remainder of the Euclidean division of k by the size of the interval, so U minus L, and then offset by L. So let's see a few examples. If k is already within the interval bounds, so for example 28, then the modulo computation just acts as the identity. If the size of the outer modulo interval divides the size of the inner modulo interval, then the inner one can be discarded. If the inner modulo is included in the outer modulo interval, then the outer one can be removed. It just acts as the identity. Also, in some cases, two modulo computations can be seen as just a translation of the modulo interval, okay, the modular ring. So here, from 2 to 4, we get 12 to 14. Last example, when we apply the unary minus to modulo computations, then it just is equivalent to applying the unary minus on the sub-expression, the inner expression, and then evaluating it on the modular ring with opposite values. Okay? So let's get back to our example. So here we rewrite the program on left in our intermediate language, where all modulo computations are made explicit. So all the operations are made over Z. So here we can see that we have SI modulo 0 to 2 to the power of 32. So if we do constant propagation, it's just 2 to the power of 32 minus 1. So what we did, what we said just before. So now we want to rewrite, as I said before. So let's consider this example where we have two integers that are x and y, and we have x that is greater or equal than y. And we want to compute the distance between those two variables, so x minus y. In fact, if we evaluated just x minus y without the unsigned int, the cast to unsigned int, it would have been an error, an undefined behavior, because x minus y can overflow, and signed integer overflow is an undefined behavior in C. So this x casted to unsigned int cannot be represented without a modulo, but the difference, x minus y, can be represented, and in fact it's just x minus y, but with the minus of z, okay? So we just rewrote this example in our intermediate language, and then we want to prove that R is indeed just x minus y, without all the modulos. So the idea is that during the inductive rewriting, at each step, we keep the information of the modular ring in which the expression has to be interpreted. So at first, this is the expression we had with all the modulo explicit. First, we apply the unary minus. So as we saw earlier, it's just minus y evaluated in the modular ring with opposite values. And then we can, because here, this modulo ring 0 to 2 to the power 32 divides its size, divides both size of inner modulo computations, modulo intervals. We can just remove the inner ones, and it's just x minus y evaluated in modulo in the modular ring 0 to 2 to the power 32. And x minus y is within the bounds of this interval because x is greater than y. So we can just remove the modulo, and we have finished our proof. We will prove something a little bit bigger by reusing the previous example as a brick. So let's consider this program. We have a variable that is equal to t1 minus x, b that is equal to x minus t0, and r that is just the sum of the two previous values. And what we want to do is to simplify it that those x cancel each other in the addition. So let's do it. We will do an inductive proof, a tree of induction rules, using induction rules. So we have what we want to prove here. And just because all the modular ring we will consider are the same, so within the interval 0 to 2 to the power of 32, and for simplicity, we will just represent modulo evaluation by underlaying them, okay? And here the color has no meaning. So let's start. We will reuse what we showed in the previous slide. That is, if you have a subtraction of two expressions and both of them are interpreted in the same modular ring as the outer one, then we can just remove the two inner ones. So let's begin. We have A. By doing symbolic constant propagation, we can rewrite it as T1 minus X, evaluated in the right modular rings. Then we can just apply the diff mod rule, okay, by removing the two inner modulo computations. We can do exactly the same with B, and then we can just rewrite in this expression the values of A and B, okay? So it does this, and we reuse again the same rule, diff mod. So we can remove the two inner modulo computations. So it's just T1 minus T0 evaluated in the ring 0 to the power of 32. And then because, again, like in the previous slide, because T1 minus T0 is within 0 to 2 to the power 32, because T1 is greater than T0, we can just remove the modulo computations and we are done. So that's the kind of rules we will use to rewrite our expressions and remove the modulo by keeping intermediate modulo evaluation during the inductive process. But we want this process to be sound. So we don't want to rewrite expression and to rewrite something that would be false, that wouldn't match the initial expression. So we will first define the semantics, of course. So we get a program state that is raw, that is just a function from variables to elements of Z. So the values, possible values of E1 plus E2 are the possible value, are X plus Y, where X is a possible value for E1 and Y is a possible value for E2. And then the semantics correction is that for a given set of properties P, if the properties P hold, then the values of E prime, when interpreted in the modular ring M, over-approximate the values of E. So this is really this inequality here, that is, we do another approximation of the values of E. And then we want to prove that our rewriting, so E can be rewritten as E prime modulo M, satisfies is sound, okay? That's exactly this equation. The problem is what happens, we would like to rewrite E times 1 divided by 0 as just 0. But is it possible? Is it possible? Of course not, because we would miss the division by 0 error. So what we do is first to enhance our syntax, our semantics. So we had this expression for the semantic, and we just will add a second term that will be the potential errors. So here, the potential errors of E1 plus E2 is just the potential errors of E1 and the potential errors of E2. Then we can see what it means for harder expression, for example, the division. Then we just have the possible values of the division, and the errors are the errors of E1, the errors of E2, and if the denominator can take the value 0, then a new error that represents a division by 0. Okay, then we have to update the semantics correction. That is, if the properties P hold, then the values of E prime, when interpreted in the modular ring M, over-approximate the values of E, when the potential errors omega 1 have already been reported. And that is the equivalent inclusion test. So let's conclude about the inductive rewriting. We automatically and correctly simplify arithmetic expressions into sum, product, and quotient of linear forms before they are passed to the underlying abstract domain that will get easier expressions. And there are many more automatic rules in the paper, more than 30, and the rewritings are proved correct. And those simplified expressions is the recognition of patterns, and that will be the topic of the next section. That is pattern recognition and simplification. And we will come back to our motivating example that is linear interpolation. So what is the linear interpolation of f? So here we have f, that is the function. In x0, it takes the value y0. In x1, the value y1. Then we have x that is between x0 and x1. And we do just the linear interpolation of it. So here in x, it will be this value. So I just represent this process into this function, this little code except, where you have exactly the same expression, y0 plus, etc. Here, we remark that x minus x0 divided by x1 minus x0 is something between 0 and 1. So when we multiply it by y1 minus y0, it's something between 0 and y1 minus y0. And yeah, that's what we would like to rewrite it in. So any value between 0 and y1 minus y0. And this would be enough to prove this assertion. And this corresponds to non-determinism. So in our intermediate language, there exist only intervals currently to represent non-determinism that are intervals. So for example, 0 to 28 is just any value between 0 and 28. The problem is that it's difficult to represent relational properties with them. So we will introduce a new operator to model non-determinism, that is the convex join. So E1 convex join E2 is just any value between E1 and E2, and the errors are just the errors of E1 and the errors of E2. And it models non-determinism, but it has expression as bounds. Why bounds like this? Because there is no order between those bounds. So 0 convex join 28 is the same as 28 convex join 0. So let's see a few examples. 0 convex join 28 is just any value between 0 and 28, so the interval 0, 28. X, convex join X is just value of X. We don't lose the information of X. And the convex join does not depend, that's what I said just before, does not depend on the order between its operands. So if X less or equal than Y is proved later, it follows that X is less or equal than X convex join Y, and that is less or equal than Y. So now we can use this new definition, new operator in our intermediate language to express properties about the example we had just before. So this part in red can be rewritten as something between 0 and y1 minus y0. Then by adding it with y0, we can just rewrite it as y0 convex join y1, that is any value between y0 and y1, and then we are done with this proof, because here y0 is less or equal than y1, so the order is fixed. So that's nice, and we can even handle more complicated patterns, like bilinear interpolations, where we are interpolating a function f that has that takes two variables as arguments. First one x and second one y, and in x I yj it takes value zij. Sorry. So we can see that this corresponds to a pattern of linear interpolation. So that's something between 0 and z00, c00. So this is a bigger interpolation that is nested, and that's again something between 0 and z00. And then we add three similar patterns. So the sum is just something between 0 and the sum of the zij. So now we know that it's something between 0 and the sum of zij, and we want to prove that it's between 0 and this. Okay, so how can we prove that? We are using octagon's domain to represent constraints that are plus or minus x, plus or minus y, less or equal than the constant. The problem is that octagons cannot represent properties, constraints about more than two variables, and there are 4 variables in this inequality. So we have a problem. The solution is to use symbolic constant propagation. So we just rewrite our inequality into, we propagate the value of r symbolically, and we get just 0 convex join the sum of the zij minus the sum of the zij, that is less or equal than 0. Then we can just simplify it to get minus the sum of the zij convex join 0, that is less or equal than 0. And then the interval domain is enough to conclude, because we know that all these zij are positive. In fact, in both Astray and our artifact, there are more refinements, and in particular, for linear interpolation patterns, if we have a strict comparison, then we get a better approximation. So we know that R is less strictly than Y1. And there are also other patterns that are handled. So in conclusion, what we propose is a cheap automatic wrapper that simplifies arithmetic expressions before they are passed to underlying abstract domains, in particular in the presence of wraparounds that couldn't be represented without it, while keeping the expressiveness of underlying abstract domains. And these simplified expressions are better to search patterns, such as linear interpolations, because you know it's product sum or a quotient of linear expressions. All those rewritings are formalized by a deterministic inference system that always terminates. And we introduced the convex join operator in the intermediate language to take advantage of relational properties while manipulating non-determinism. And this domain has been implemented in Astray, at least the ENS version, but also in an available toy abstract interpreter powered by Apron that you can see, you can find on Zenodo. Thank you.
Thank you, Jérôme. Are there any questions? Yes, question in the back. One moment, I'll pass you the mic.
So, thank you, that was very interesting. I have a question. When do you decide to introduce your operator? Because both forms have different characteristics, so you can you are going to lose information when you rewrite it in your expressions. So what's the criterion?
Okay, that's a good question. In fact, we had already in mind at the beginning that we wanted to prove properties about linear interpolations. That was really a motivating example. And we already know what we wanted to assert at the end, what properties we wanted to prove. And to prove this property, we had to represent non-determinism, but with relational properties. Okay? So at first, it wasn't like this. It was a bit different. It was another operator that was something that was taking one argument, that was an expression, and that was representing something between 0 and this expression. And then we iterated a bit and found out that it was better to represent the convex join. And that it could be maybe interesting also on other applications, on other, to represent other properties.
Yes, one more question, one moment.
Yes, thanks for the nice talk. I was wondering if the rewrites always improve precision, or if there are some cases where the rewrites lower precision of the overall analysis, and how do you deal with that? And
yeah, thank you. Okay, so because we are rewriting, I mean, it depends on the other abstract domains, because for example, for the linear interpolation, it rewrites it into, here, y0, convex join, y1. But if by another way we could find properties about x0, x1, and about x, where it is in between, maybe we could get better approximation. So that's not always the best representing the best properties, but I think for to get those invariants, it's really convenient.
Thanks.
Any further questions? All right, then let's thank you.
I think it's just another.
Oh, sorry.
Hi, I mean, I would be interested to know, I mean, and you can be quite rude about this, it's fine. So we had a paper in SAS and it was about taming the wrapping of integer arithmetic. And we had a wrapper there which operated on general polyhedra. Okay. Is it that you found that wrapper failed to work for linear interpolation, or was it sort of too weak for that?
You mean polyhedra?
Sorry?
Is the polyhedra domain?
No. It's we had a wrapper that did a form of relaxation, which actually took a polyhedra and relaxed it with the
taming.
Yes,
I see
right.
the okay.
Yeah. Okay. So is that method too weak for applying linear interpolation?
I think so. Let me think a bit. But I think, you wouldn't represent. So what would you have with this? You would have a division of. Yeah, no, you wouldn't have something precise enough because you want here to recognize that x minus x0 divided by x1 minus x0 is within 0 and 1. And this couldn't be, I don't think this would be expressed by the polyhedra even with the Vera.
Okay, that's good. Thank you.
All right, any further question? This time really not, so let's thank the jury. And then the next presentation I think will be Andy King. And also about modular arithmetics.
I know, it's the theme, isn't it?
All right, here you go.
Thank you. Okay, so I'm going to talk about modular arithmetic. And the title of this paper is Polynomial Analysis of Modular Arithmetic, and the title is sort of carefully chosen to have a sort of doff the cap to a influential paper that was written by Marcus Müller-Ohm and Helmut Seidel on the analysis of modular arithmetic. And it's work that was done chiefly by two of my students, Tom Seed and Chris Coppins, with help with Neil Evans, who works applying verification to microcontrollers. Okay, so if you are of a particular persuasion, you can do a lot worse than entertain yourself by reading a book called Hacker's Delight. So Hacker's Delight is a compendium of fascinating and entertaining algorithms, and it is quite sobering because you can apply sort of textbook techniques to lots of these very simple algorithms. And lots of the methods that are so precious to us fall over in subtle ways. So this is a simple algorithm, and I've called it MI because it calculates a multiplicative inverse. So given an integer a, the function will return an integer x. And the crucial property is that if you multiply a by x, the result is 1 modulo 2 to the power of 32. Now what you have to do here is you have to interpret your signed integers as unsigned integers to make sense of that. Now I think what is fascinating is that conventional methods, and there are lots of these that reason about nonlinear systems, are inadequate here because we have an interaction between the integer and modular properties of the program and the nonlinear properties, and clearly the domains that just express modular properties in a linear setting are also not adequate to even deal with a simple program. Okay, so programs like this are not quite the motivation for the work, but I'll talk about some more motivation later. But I think that's an interesting motivation for the first part of the talk. So here I've got like a sort of unpotted history of, if you like, a timeline of work that's fed into our work. There was the Marcus Müller-Ohm paper from 2005. It was an ESOP paper and then a Toplas paper. And there was also a paper by Deepak Kapoor, and that's another influential paper that we're going to build on. And in that setting, the invariants were systems of polynomials where the coefficients were rationals, and Grosvenor-based techniques were used there to formulate, in particular, a join operation and a variable elimination operation. And we're going to take those operations off the shelf and use them in this setting without any more comment. Now, a particularly interesting paper here is a SAS paper in 2008 by Andrea Flexiter and Michael Petter, also with Helmut Seidel, and it was about the inferring systems of polynomials, again, the context of modular arithmetic. And I think this is a sort of very telling paper because it sort of indicates the delicacy of working in the modular setting. So let me comment on this, and I think this is another sort of sobering comment on how tricky this work can be. So in this particular paper, the force of the work is to build a system of weakest precondition transformers in the context of negative guards. So if we look at this sort of top line here, what we've got is a negative guard, and the way to read this is that P does not equal 0, that's the guard, and then we've got a condition expressed as a polynomial Q that we have to satisfy, and we want to infer another polynomial such that if that holds before the guard, then the guard filters out values such that the values satisfy Q. Now you can be forgiven for thinking, because this is the way things work in a field setting, that the weakest precondition here is P and Q, is the product. But when we work in a sort of modulo setting, we can have a sort of tricky problem here, because the precondition can vanish, it can reduce to true, and that can compromise the soundness of the approach. And this is a very subtle thing that can happen in the peculiar case of the modular setting. So, for example, if we set P to 2x, okay, and Q to 128x, then their coefficients, when we multiply them together, are 256. So if we work modulo 256, the product PQ vanishes to 0. And any assignment will actually satisfy that product. So if we choose the particular assignment x equals 1, that satisfies the polynomial 0, or 0 equals 0. So that passes the disequality, but actually violates Q. So I think that's really, really intriguing. But don't think that I'm sort of dissing this paper. I've got a lot of respect for this paper, because I think it points to important ways of taking our particular work forward. But it does indicate that how tricky it can be to work with negative guards in this particular setting. In our work, the main contribution is looking at negative guards and positive guards. Okay, so just to whet your appetite to some more, again for sort of entertainment, it's also sort of worth commenting on how rich the domain is in terms of expressing joins. Okay, and I think this is really quite intriguing. So we've got two systems here, P1 and P2, indicated in red and blue respectively. And if we look at the solutions to these systems, okay, we get 2 points, 2 red points and 2 blue points. Okay, and if we calculate the join as specified in the Deepak Kapoor's paper, lifted to the setting of modular integers, we get a join that adds 2 further points. So it's quite an unexpected join, but I think what is interesting is we don't populate the whole space here as you might expect with values. So when you work with modulo integers, you get very rich joins. Okay, and it's also telling to see that the join here is expressed also as a system over 4 polynomials, and each polynomial there is no worse than cubic degree. Okay, so when you calculate the join, often you don't end up with these huge unwieldy systems. You end up with systems which are often the same size, but with a lot more expressiveness. So I think this is a very interesting and tantalizing domain to actually work with. Now, I think the most perhaps important part of this domain, and this was the motivation for the work, because we were interested in microcontrollers. Neil Evans was interested in reasoning about bit-level properties for the analysis of 8-bit microcontroller code. Okay, and I think the main value of this particular abstract domain is that it satisfies the ascending chain condition. Okay, and the force of this is that it allows us to calculate systematically best transformers for some completely wacky sequences of operations to get some very interesting abstractions, to give like a very tractable way of reasoning about sequences of bit-level operations. And here's a particular example. The first thing I want us to see is, first thing I want us to observe is that when we work in this setting, when we have systems of polynomial equations where our coefficients are modulo a power of 2, we end up with a finite domain. Now we can actually see that, okay, because if we just think about how many points we would have, let's think concretely to make this easy. Let's suppose our bit width, and henceforth we're going to call our bit width omega. So let's suppose our bit width is 3. Then how many points can we have? Well, Z8 has 8 points in it. Working over 3 variables, we can have 8 times 8 times 8, 512 points. So in a sort of the most concrete domain we can have would be 2 to the power of 512 points, which is, of course, finite. Okay, and we won't be able to represent all those points with systems of polynomials. So that means it means that the numbers of systems we can have is also finite. Therefore, we must satisfy the ascending chain condition. And we can use that to compute best transformers. Here's one we computed earlier. So it's a best transformer for Z is equal to the bitwise and of X and Y, just over 3 bits to fit on a slide. And it's this monstrous and quite unexpected system of polynomials here. Now, how can we actually compute this? Well, this is not our work, but we sort of leverage off it. And I would go so far as to say that the particular domain really adds legs to this work of Tom Reps. It was an algorithm that appeared in VimKai, and it's a best transformer algorithm. Okay, and here I'll just give a synopsis of his algorithm so you can see how it fits into this setting. Okay, so let's suppose we've got a symbolic representation of a particular operation, and we call these things these days SMT formulae, right? Okay, and you can get like a whole load of low-level sequences of our machine operations, transform them into SSA, and then encode that with an SMT formulae. We do that all the time. And then we've got this iterative algorithm here, which computes a best transformer for this relation. So how does it work? Well, we iteratively relax our system of polynomials P. So firstly, we set P to be an unsatisfiable system. That's a polynomial system which has just got one polynomial in it, 1, which is unsatisfiable. And then we've got a loop variable. Now, what's the key idea here? Well, what we do is we take our symbolic formula that we want to over-approximate, okay, and we take the best abstraction that was calculated thus far, which is P, and we encode P and therefore its negation as an SMT formula and encode that with phi. So when we present that to a SAT solver, what we're asking for is a solution of phi which is not yet represented by our evolving abstraction P. Okay? And if there is one, because we're using a complete solver, we get a set of bindings. We encode those bindings as a new polynomial Q, and then we relax P with Q to get a new system of polynomials, and we keep going in this fashion until we don't get a solution, and then we reach our fixed point. So it's a completely automated way of working, but it only works when your domain satisfies the ascending chain condition. And I think that's the real power of what we got here, because it plugs in with this method beautifully, and we found it to be useful in practice when we reason about microcontrollers. Okay, so let's talk about the domain a bit, and then I will then talk about some of the domain operations, in particular the sort of novel aspects of those domain operations. Now, what I'd like us to see as a take-home message is that the key operation that's used in many of our weekly relational domains, namely closure, carries over to this setting. So we've adopted that architecture here, and we've reduced lots of operations to closure, and the key computation problem is actually computing closure, and with that in place, we build a whole edifice of domain operations, which we then plug into our abstract interpreter. Okay, so let's just think about what our concretization operation is first. So we're going to take P, and P is a system of polynomials. So let me just explain the notation here. So Zm x is the set of all polynomials over the variables x, where the modulo is m. Okay, that's the way to read that. Okay, and the interpretation of P is just as the set of vectors, right, such that when we evaluate a small p, a polynomial from big P, okay, that polynomial vanishes with the vector a. So we substitute, if you like, the value a1 for x1, a2 for x2, and so on and so forth. We evaluate p, and if the result is 0, then that p describes the tuple of integer values a. Okay, and this gives us our concretization operator. On top of that, we can build our closure operator, at least in a theoretical sense. Okay, so what's our closure operator here? We're going to take a set of polynomials and we're going to enrich it, okay? And taking our sort of lessons from octagons, we're going to throw in all the polynomials which are actually entailed by our system P. Now, what does that mean? Well, we take our system P, we concretize it, okay, to get all the solutions, and we build a set of P's, little p, I just should have used a different notation here, where the system P has a characteristic property that its solutions enclose that of the system big P, okay? So I bundle up all the P's, which are entailed by big P, and that's our closure. And now we're just defining things in a theoretical way. And the value of this is that then we're not burdened by the fact that we can rewrite our systems of polynomials in different ways. This gives us a canonical representation. It's an infinite representation. It's a massive system of polynomials, but at least we've got a canonical representation. Okay? And with that in place, we can build an abstract domain that turns out to be a finite lattice, and we enjoy the sort of properties that we really like. We've got a Galois insertion, and in particular, we're not lumbered with magicking up a widening. Okay, that's fine. Well, I hear what you're saying from the floor. You're thinking, well, this is fine, but all that guy's done is turned one difficult problem into another difficult problem. That's working with his massive set of polynomials. And I'm going to respond to that now. And what we're going to do is we're going to use bases, which are a finite representation of these otherwise infinite sets of polynomials that are closed systems. Okay, so what do we need here? Well, we need here the notion of an ideal, okay? So what's an ideal? Well, an ideal is a set of polynomials that's closed under addition. Okay, so we can take any two polynomials in our ideal, we add them together, and that's also in our ideal. We need that property. And the ideal must also have the property that if we take any polynomial in our ideal, and if we scale out that by any polynomial that's not necessarily in our ideal, that's also in our ideal. Okay, so that's what an ideal is. Now, the cool thing about our ideals is that we can represent them with small, compact, finite sets of polynomials, and we use the notion we use the notion of a basis here. So if we've got a set of polynomials B, what we can do is we can generate, and that's what we mean by this. We generate an ideal from B by, guess what? Taking all the polynomial combinations, adding things together, and doing various scaling. This generates this uber big infinite system, but crucially, we're representing this ideal with a compact finite system B. Okay, so that's the tactic that we actually recover tractability. Okay. Right, okay, with that in mind, let's go back to the problem that we used to set up this talk. And it's, I've got here the flow graph of MI. I'm going to just use this to sort of work out the operations we need to support, at least to reason about this particular program. Okay, so what have we got? We've got assignments to constants, assignments to variables, assignments to polynomials, not surprisingly, and we've got assumptions, which are both positive guards and negative guards. Okay, now, what we've done here is we've actually reduced the problem of verifying that AX equals 1 to a reachability property, okay? So if node 7 is not reachable, okay, then the only path is to node 6, which tells us that AX has to be equal to 1. So that's the way we've reduced this to a reachability problem. Okie dokie. So with that in mind, what we're going to do is we're going to try and build these operations at the top, okay, using algorithms at the bottom. I'm going to work up this lattice against the directions of the arrows to build things. I'm going to give you some insight as to how our architecture fits together. And I'm not going to talk about joining, I'm not going to talk about elimination, because we're just adapting previous work to our new setting. Okay, the thing at the bottom is a Grosvenor base. So let's talk about Grosvenor bases in people spend their whole career talking about Grosvenor bases, but I'm going to do it in 2 slides. So I apologize if I upset anyone here for my glib statements. Okay, so I think the simplest way to understand a Grosvenor base is to think about the notion of reducibility. Okay, so we can say that one polynomial is reducible by another. P is reducible by Q if we can eliminate the leading term of P by subtracting multiples of Q. Now, that is a comprehensible notion, I believe, and we can see that with an example. So let's suppose that P takes this form, it's 2x squared plus 3y, and Q takes this form, 2x plus y. We can see what the leading term of P is, that's 4x squared, right? And we can eliminate the leading term, 4x squared, by multiplying P in a particular fashion, i.e. by minus 2x, okay? adding the multiple of Q to R, and in doing so, we eliminate the leading term, okay? So here we're doing a form of reduction, and this might feel Knuth-Bendix-like if you've been in those AI courses, okay? And that's because what we're doing here is we are like deriving a polynomial that is strictly smaller. We need this to actually get a determinating algorithm. Okay, so that's the idea of a reduction, and we can use that to stipulate what we mean by a Grosvenor base. There are lots of alternative definitions, but we're going to run with this. So we can say a basis B, a set of polynomials, is a Grosvenor basis, okay, if we take any non-zero polynomial in the ideal generated by B, okay, and P is reducible by one of the polynomials in the basis, a PI, okay? Now, what we can do, and it may seem surprising, is that we can take any system of polynomials, we can crunch them through an algorithm, and there are lots of algorithms that do this. Probably the most famous is Buchberger's algorithm, and that can produce for us a Grosvenor base. So a Grosvenor base is derivable from any system of polynomials. And this gives us some sort of wonderfully useful properties. I mean, one way to think about this is that a Grosvenor base is a bit like doing triangulation. It's like triangulation of a system, not a linear system. It's like triangulation on steroids, because it's working over polynomials. Okay, and once we've got a Grosvenor base, then we can check various properties. And you can see where they'd be useful from a sort of abstract interpretation perspective. What we can do is we can check to see if a polynomial, right, is contained within an ideal, and do that in a computable way, even though the ideal is an infinite object. We can check with one ideal is contained within the other. I mean, I know what you're thinking. Oh, that would give me like a fixed point check. That's dead good. And we can also eliminate variables from an ideal, and that's useful for projection and for variable assignment and things like that. And you can even do things like rationalize or revisit bit blasting using Grosvenor bases and compute a much denser bit blasted version of a bit vector formula using Grosvenor bases. And we got a paper on that in SAT last year or the year before. So lots of useful things you can do with Grosvenor bases, and they fit surprisingly well in the sort of modular setting. Okay, so that's the background on Grosvenor bases. It's got a tick, we're moving forward, stay with me. Okay, so let's go up to covering now. So covering is like one of the key operations that we do. We really want to get to closure, because that gives us our stuff, but we decompose closure into an operation called covering, and covering here, is a bit like a partitioning operation. I'll explain that intuitively. You can go to the paper and you can see there is an algorithm for that, and it uses Grosvenor bases to do a form of forward checking, if you recognize that terminally from constraint solving. Okay, so here's an example. We've got F1, it's a system of two polynomials, right? Okay, and we can think about the solution set for F1, which is of course given to us by our gamma. We've seen that already, and it's this set of points here. Now, what's a covering for F1? Well, a covering for F1 is a set of tuples of polynomials that give us a parameterized representation of F1. Let's just see how that works. So the first thing to note is that we've got our points, our concretization of F1 here, and we've got a set of points here, A1, A2, and A3. And if you look carefully, you will see that if we union all the points in A1 and A2 and A3, they give us the concretization of F1. Let me just try and convince you with that informally. Okay, so let's scan the concretization right to left. We've got this point here. We can see that it's there. Then we get these 2 points here. We can see they're there. And then we've got that point there. We can see it's there. And I hope you get the idea. We've got all the points in the concretization, but no more. Right. Now, what I want us to observe now is that we can represent these points of A1 and A2 and A3 in a particular parameterized way. Okay, let's look at A3 first, because that's simplest. Okay, A3 is just 2 points, and we can represent those points as in terms of a parametric variable W, W1, which ranges over all the modulo variables between 0 and 15, okay? Okay, and if we were to plug these values into the second position of the second coordinate, this linear function, you can see that if we plug in 0 here, we get the value of 7. We get that one there. If we plug in the value of 1, we get the value of 15. And any other values, we also get 7 and 15 and so forth. Okay? And the first polynomial here is a constant. Okay? And if you look at A1, that's a bit more elaborate. Here we've got two polynomials, both of which are functions of W1, and W1 ranges over all the integer variables. Okay, so the take-home message here is that a covering is a set of tuples of polynomials. Each polynomial is itself defined in terms of a parametric variable, but not necessarily one. Here's an example here where we've got a covering for this space, okay, and it's defined in terms of two parametric variables. Okay. Now, perhaps what's surprising is that we can actually compute this decomposition accurately and even efficiently. And we do that by virtue of the fact that we can use Grosvenor bases to work out how we can divide up our space. Okay, some more of that in the paper. Okay, so that's the intuition behind the notion of a cover. Right, but what we want to get to is the notion of a closure. Okay, we want to get a finite representation of all the entailed polynomials so that we can compute our join. Right, and for that we need a bit more stuff, I'm afraid. Thanks for your patience. What we need is something, the notion of a null polynomial. And we thought we'd found something new in terms of a null polynomial. A null polynomial, to use our terminology, is a polynomial that is vacuously satisfied. So here's a system of null polynomials, and you will see what I mean. Let's just look at this critter at the end, 8y squared plus 8y. Here the modulo is 16. And you can see that this polynomial is satisfied when y equals 0. The whole thing vanishes to 0. But also when y is 1, because we get this part becomes an 8, that part becomes an 8. Modulo 16, that's 0. But also when this is a 2, right? And also when it's a 3, and so on and so forth. So these are polynomials which always hold, irrespective of the assignments on our variables. We call these null polynomials. And in fact, null polynomials arise in encryption. So people have studied these extensively. And there's even a way of systematically enumerating the null polynomials. And perhaps more surprising still, there's even a way of systematically calculating a Grosvenor basis for the null polynomials. Okay. And we're going to make use of that. That's a paper in the Journal of Symbolic Computation. Okay, so with that in place, we've got the null polynomials, we've got our covering, now we can compute the closure. Okay, so let's do it in terms of this example. F, and we can pick up the details in the paper. So we're going to calculate a cover for F using the sort of techniques that I've pointed out on the previous few slides. And we're going to have a covering which breaks into three parts, where the first part is a tuple of polynomials. Okay, they're in terms of one variable, W2. Okay, we're going to generate the basis, N, for the null polynomials for a particular variable set, W2, and also for a particular modulo. Okay, and with that in mind, what we do is we're going to do a form of projection, which, if you like, morphs together our null polynomials, okay, using a relationship that we set up between our covering and each of the variables in our system, x and y. Okay, so just to give you an intuition of what's going on, this polynomial here is asserting that x is equal to this term. This polynomial here is asserting that y corresponds to this term. That's what these two polynomials mean. We add them to the system of null polynomials, and then what we do is we project out W2. So what I want us to observe at this state, we can do all these things because of the machinery that we got. And when we do that, we end up with a Grosvenor base which takes this particular form. And for reasons that are explained in the paper, it will infer for us those entailed equations that we're actually missing that are needed in our closure. We can do up the other things as well. We sort of join them together, and if we do the results, then what we do is we end up discovering these missing polynomials that we didn't have before in our system that contain just two polynomials. Okay, so the take-home message is probably all that you can deal with at this point is that if we've got covering, and if we've got null polynomials, and if we've got variable elimination, we can use that to build a closure operator. Okay, which is what we need for our domain operations. So then we've got our closure, and then on top of that, we can build our various domain operations. Let's just talk about our assumptions, and then I'll sort of close up. Right, okay, so how do we deal with our assumes? Well, what we do is we've got the system that we got described thus far as our state. It's a big system P. We add our P to it and then compute the closure. We've got all those components in place. But we can also deal with negative guards using a trick here, which I think is utterly devious, and I am proud of, it must be said. So what we can do is we're going to observe that if P does not equal 0 under some sort of variable assignment, it means that P must evaluate to a value which is non-zero, okay? Now, because we're in a finite setting, it must mean that that non-zero value is integral, okay? And there must be a least bit in that integral value which is 1, and there'll be all zeros to the left of it, okay? So let's just suppose that that 1 bit is occurring at position k. Well, if it's occurring at position k, then what we can do is we can take that value and shift it by omega minus k bits. That will multiply it by 2 to the omega minus k. We'll end up with a value that's 1, 0, 0, 0, 0, 0, 0, okay? And that value has to correspond to the value 2 to the omega minus 1. We don't know what k is, so we've got to consider all values of k, but using this argument, we can reduce a negative guard to a positive guard, which of course we can actually model. So that's cool. So you can see the scaffolding we've actually got going on in this stuff. We're building what we want on successively more and more complicated objects, and the algorithms are in the paper. Okay, so we got the bits, and I'm not talking about the other elements because they are more standard. Okay, so let me just finish up. So what have we got? We've got an abstract domain, the modular polynomial abstract domain that satisfies the ascending chain condition, and that's just really good for calculating best transformers. I think that's the real value of this work. Okay, and we can use it to find invariants we didn't have before, but perhaps that's no surprise. We've introduced a closure operator for MPAD, and that's doable and it's calculatable. We built it into a system and it works. It needs a little bit of tuning, but in other words, you need to reflect on how Grosvenor bases are calculated, and we make comments on that on the paper. But you can get a reasonable system, and we can calculate invariance in this program. I think it's now up to 32 bits in less than a second, so that's okay. And we support positive and negative guards. And perhaps one interesting sort of unexpected take-home from this work is that in the paper we describe a way of reducing the complexity, the size complexity of polynomials using a reduction technique that seems to be new to computer algebra. So that's a nice feed from abstract interpretation to the world of computer algebra. And on that note, I will stop.
All right, we have time for some questions. All right.
Hi, so thanks for the super interesting talk. And I was curious to hear a little bit more about the covering, if you could give some intuition. The covering, if you could give some intuition of how you choose the pieces of your covering and how you are actually able to compute that.
Okay, so the intuition is that if we have a system of polynomials, okay, what we can do is we can just choose a particular bit in one of the variables, and we can assign that bit to either a 0 or a 1, and that partitions our system into two systems of polynomials which are disjunctive. Okay, that's it. We actually do that in an intelligent way so that we don't get lots of divisions. So we don't, in fact, what we do is we take our system of polynomials, we calculate a Grosvenor base, okay, that tells us a sort of good splitting point. So it's a bit like forward checking, okay? We sort of do a split and we apply this tactic recursively. Does that help?
Yeah, thanks.
Right, the next question.
Yes, I was wondering if you had implemented this system and what is the well, maybe the theoretical time complexity of the operation that you present, but also the practical complexity, for instance, on the example that you show, the motivating example.
Okay, well, I think I'm going to try and skirt that question, not because I'm being devious, but I think it's, in one sense, the wrong question to ask, okay? And what I mean by that is that we are here using a classical algorithm for calculating Grosvenor bases. And you know, Grosvenor bases algorithms have, it's well known they have double exponential complexity for solving particular problems. But it's a bit like SAT, right? So in SAT, what's happened is that you know, we have rapidly evolved from the point we can only deal with 100 variables, now the point we can deal with 100 million variables. And it's a bit like that with the sort of Grosvenor base algorithms. So in the last decade, there's been incredible evolution of methods. And in our paper, we just talk about using sort of one classical technique, and it's called the Grosvenor-Muller rules. And the Grosvenor-Muller rules reduce the number of what's called S polynomials you calculate. Now, we sort of implemented this, and we had like a 4-bit problem. We were working on 4-bit problems initially, and our fixed point was taking over a day to reach a fixed point. We applied these rules, and it brought the running time down to less than a second. So, you know, I don't think, and that is like a standard rule. So I don't think we can sort of underestimate the value of the techniques that are out there in the computer algebra literature. So I don't think it's helpful being obsessed with the complexity, because the complexity is horrendous. But because now these Grosvenor-based solvers are so powerful, and we can just think of them as being a bit like a sort of SAT solver. And it's worth noting as well is that, you know, we are just using like very old 1960s technology, which was specialized to the modular setting, which we've added the Grosvenor-Muller rules to, which we haven't written up yet, because that is research that we haven't written up. But because that requires quite a lot of analytical proof work. But on top of that, there were these what's called F-series of algorithms, like F2, F3, F4, and F5. And these are like super efficient algorithms. So their orders of magnitude faster than Buchberger's algorithm. So what we should have done in hindsight is to start with them, right? But hey, we didn't know about them at the time. Is that okay?
Yeah, I understand that the theoretical complexity can be quite different from what happened in practice, but I was wondering if there were already some cases where you could apply your technique in practice. And
Yeah, we could actually. So we could adopt a different representation of our polynomials. So there we can actually bound the degree that we're actually working in, and we could derive a complexity bound that way. I don't think that would necessarily be the best use of our research time. And the reason is that there is a method that we just hint at in the paper where we can actually, which is like a runtime version of that, where we reduce the degree of our polynomials. So that seems to be a lot more sort of powerful method, again. So I'm going to push back on that, because I think, you know, in computer science, there is this thing that we've been obsessed by complexity, and that's actually stopped us doing things. And I think we're in real danger of sort of making that mistake in this setting.
Okay, makes sense.
Is that okay? There we go.
All right, then let's thank the speaker again. So the last talk will go down from polynomials to octagons, and it will be held by Michael Schwarz from TU Munich. So let's welcome the speaker.
All right, so welcome everybody. Thanks for attending my talk. Today I'm going to present some work that is joint work with my supervisor Helmut Seidel. And we're going to go, as we've already said, to weakly relational domains. The conventional wisdom is that they offer a good trade-off between precision and efficiency, and for this reason have been widely used in static analyzers. And one that we've already heard of a couple of times today is the octagon domain, which is one that is particularly common. It was invented by Antoine Minet somewhere in the early 2000s. For those who do not know, when you have an octagon, what you have is you have a conjunctions of inequalities of this form plus minus x plus minus y is less or equal than some constant c, where c in this case here would be from the integers. So an example octagon value might be something like this, where you say minus x is less or equal than minus 5, x is less or equal than 10, and then you also have some constraints on the sum of x and y and the difference of x and z. Alternatively, if you do not want to talk about integers, you can also talk about octagons that range over the rationals. In this case, your constant would also be replaced with a constant that comes from the rationals. A key operation that one needs to do with octagons is called normalization or closure. And the idea is that one tries to make all the implied relationships explicit. And this is needed, for example, to efficiently check equality, inclusion, and a couple of other operations. Let's take a look at an example here. So if we have this octagon value here, we actually have some additional relationships that are implied. Namely, if I take these two together, then I get an upper bound for the value of y. And if I consider those two, then I additionally get an upper bound for the value of minus z. And this value that we have here would then be closed. Now, the complexity of this operation was already known right from the beginning, that it's cubic for octagons over the rationals. And then a bit later, or 7 years later, it was shown that it's also cubic for octagons over integers. And Enea is one of the co-authors of this, so he's actually here. And what all of these algorithms have in common, the proofs, is that they tend to introduce auxiliary variables minus x for the negated value of the variable. And then they all employ some sort of all pairs shortest path algorithm, such as Floyd-Warshall algorithm. And our idea here was somehow that we wanted to raise the abstraction level of these proofs to maybe get at more concise proofs. And particularly, we somehow wanted to avoid introducing these auxiliary variables. And let's first get a bit of notation out of the way. So when we say R, this is a relational domain, then we have some set of variables X. And what will be of particular relevance later in this talk are the clusters of size at most 2. So this is what we mean when we write this X in these square brackets sub 2. So this is all subclusters that have 1 or 2 elements. Then we're going to be dealing with assignments later. So this we don't denote like this, where we say we assign to a variable X some right-hand side E. And we also deal with guards. This we denote by this question mark C. And then last but not least, we also need to deal with an operation that we call the restriction. And basically, this amounts to forgetting all of the information about the variables that are not in this Y. And then sometimes we will also use this notation, so R superscript Y, to talk about these values that only contain information about variables from the set Y. And basically what this means, if I take a value from this and I restrict it to Y, then I end up with the original value that I had. So back for some ESOP paper, we at some point made this observation that any relation can be approximated by meeting together its restriction to 2 clusters. So this equality here holds. For some domains, however, one can do better. Namely, one can have some domains where one can give all values of the domain basically as the meet of these restrictions. So one doesn't lose anything by considering only these restrictions to 2 variables. And this then we dubbed to be 2D composable. This is the first property, and the other property that one needs for a domain to be 2D composable is that all the finite least upper bounds can be computed cluster-wise. This is this property that we have written here. And then we would call basically this restriction to these 2 clusters the 2 normal representations, a bit of notation again. And for octagons, this then corresponds to the strong, respectively the tight closure, this 2 normal representation. Now, our idea was maybe if we have this 2D composability, we can already do the efficient normalization. And we got inspired by all the previous work that uses some sort of all pairs shortest path algorithm. So we tried to apply the Floyd-Warshall algorithm here. And the idea would be that we would be given some values that talk about these 2 clusters. And then ideally, the algorithm should compute the 2 normal representation. We discovered quite early on that this does not work right off the box because we have these single value clusters that only talk about 1 variable, and they somehow destroy this here. So one needs to add an additional initialization loop before. And then this approach seems to work for the octagons. However, we had a very, very hard time trying to prove that this actually computes the normalization for all of these 2 decomposable domains. And then at some point we decided, okay, maybe we should also consider if this is maybe not true and we're missing something here. And it turns out there's a counterexample. So there are 2 decomposable domains where Floyd-Warshall does not compute this 2 normalization. So let me very quickly give you this counterexample. So it's a very simple domain. We basically here fix the set of variables to be 4 variables. They range over values from this set 1, 2, 3. And as the abstraction of these concrete values, we consider maps from variables to sets of these values. So for example, one could imagine an abstract value given by these clusters. So in the Rx cluster, we know that A is in the set 1, 2. In the AY cluster, we know that A is in the set 2, 3. And in the AZ cluster, we initially know that it's in the set 3, 1. And all of the other clusters initially are top. And now the 2 normal representation of this should be bottom in all clusters, because if I do the intersection of all of these sets, then I find out that actually there is no value for A that satisfies all of these requirements, and therefore the value should be bottom. And let's take a look at what the Floyd-Warshall algorithm actually does here. So first of all, we have this initialization round. In this case, it does nothing because we do not have any interesting values in the single clusters. So this is done. And then we try to make all of the improvements explicit that happen via this A variable. So what happens here is also nothing. And then we consider the improvements that happen via X. So basically, we consider if I go from A to X and X to A, what is the value that I get then? And then I project it to just A and meet with the value I had before for A. So we would end up with this. And then we can sort of do this for all of the improvements that happen via X. For these other columns here, I do not need to do anything because they are top, and I'm always projecting on things where the A does not appear. So the only way they will change is if it becomes bottom, any of these values. This was the round for X. Then we do the round for Y. We have some improvements here, again, in these clusters. And then we have at Z, we then get the value that it's bottom, so for this AZ cluster. Then we propagate all of the improvements that can be made via Z. So then we end up with this value here, where we have computed the 2 normalization for all of the values, for all of the classes in which A appears. However, the algorithm is now done. So we stop, and we have the problem that for this example here, our algorithm has failed to compute this 2 normalization because we have tops everywhere here. So actually, 2 decomposability alone does not already make this efficient normalization possible. So then we tried a different angle and considered this 2 normalization via a constraint system. And once again, here we are given some abstract relation R that is given by these 2 clusters. And we introduce unknowns for each of these 2 clusters. And basically, we try to write down all of the improvements, or the constraints correspond to the improvements that can be made. So we consider the initial value for xy, and then we consider the improved values if I go via z for all of these variables that appear here. And then we have a small proposition here, namely that the 2 normalization is a solution of this constraint system. This can be verified quite efficiently. You just plug it into the constraints, and you immediately get it. And the consequence of this is that if there is a greatest solution, it is an over-approximation of this 2 normalization. And then we had this observation that what we do when we do this normalization via the Floyd-Warshall algorithm, we actually perform steps that are similar to the things that the constraint system does, provided that one at some point stops considering intermediate improvements that happen via some of the variables in there. And it appears as little as if these variables were projected away, because I'm not considering the improvements that happen via them anymore. And this inspired us to define another property. Namely, we can say that some 2 decomposable domains are additionally 2 projective. And we say it is 2 projective when each variable can be projected away using projections onto clusters only. So what do I mean by this? So let's say here I have some relation that is given as the meet of these clusters, and it ranges over some set of variables y and some variable z that I want to project away. And here these yi's, they are from y, or they are this variable z. And then these r sub some cluster speak about values in this cluster only. And this R prime simply speaks about all of the values that are in this, speaks about variables in Y only. And then I say this thing is 2D decomposable if I can do the following. I basically keep the R prime as it is, and then I try to eliminate the variable Z by considering all of the combinations that I can make between clusters involving C and clusters involving other variables. So this would look something like this. And then our claim is that for these two projective domains, there is a greater solution of this constraint system that we have considered before. For these domains, this greater solution coincides with the two-normalization, and we can actually efficiently compute this by the Floyd-Warshall algorithm. So I just give you a short proof idea of how one might decide to show this. So first of all, we fix some order on the variables. So we just say the variables now go from x1 to xn, and then we define x sub r to be all of these variables with an index in R. And x sub r bar is basically the complement of this. And once we have defined this, we define a sequence. And in the sequence, we say, okay, for the 0th iteration, for all of the clusters, I just meet it together with the single variable clusters that appear there. And then all of the subsequent iterations, I basically make the improvements explicit that happen via this xr. And I do this for all r greater than 0. And then the idea is that once I have made all of these improvements explicit, this xr does not need to be considered anymore. And we remark here that each step in the sequence actually corresponds to evaluating one constraint of the constraint system. It's going to be important a bit later. Okay, so then our proposition here is if I have this S bar as the abstract relation that is represented by this S sub p, then for the elements of the sequence, in the sequence, the value for this cluster will always be smaller or equal to the value for all the single variables that appear in the cluster. And then the last statement is that basically I can represent the value by meeting together all of these subclusters for the R's that I have not eliminated yet. Let's take a look at what this, or how one would prove this. For R equals 0, it basically holds by definition. There's nothing to show here. For R greater than 0, we do it by induction. And the key step here is that one uses two-projectivity to be able to consider these meets in isolation. Now, this is the proof. I only put it there because we claim that we have an elegant and short proof, and this is the entire proof of this complicated step. I will not go through it and bore you with it, but I just wanted to put it there. So what is the consequence of this proposition? Well, interestingly, if we actually set k equals n, then we have now, as a consequence of this proposition, that the normalization in this xy cluster is equal to the nth iteration of this of the sequence for the xy cluster, meeting this together with the values for the single variable clusters. And because of our first property from the proposition, we can show that this is basically equivalent to the value of this xy cluster in the nth iteration. Okay, so then let's return to the Floyd-Warshall algorithm here. We basically now need to somehow relate this to the sequence that we have constructed and the constraint system that we have constructed. So let's once again consider some input collection and this S bar, which is the normalized value, and then TP, we call this here the result of this Floyd-Warshall algorithm for this input collection. And then the claim is for any of these two clusters, the two-normal form is less or equal than what this Floyd-Warshall has computed. And the second claim is that the two-normal form is greater or equal to what the Floyd-Warshall has computed. So basically the claim here is that they are actually equal. How do we show the first thing? Well, the idea is here that the constraint system that I was showing you earlier, all of the right-hand sides of this constraint system are monotonic, and each update of the Floyd-Warshall algorithm corresponds to evaluating one of the constraints. So whatever this algorithm will compute is greater or equal to the greatest solution of the constraint system. And before we have shown that this greatest solution over approximates the 2 normalization. So this is the first property here. And then the second property, we show this by induction. And namely, what we show is the value in the kth iteration of this Floyd-Warshall algorithm is less than the value in the kth sequence that we have constructed before. And then we have shown these two to be equal here. So now what do we have? Well, we have that the normalization is cubic, provided that we have R that is 2 decomposable and 2 projective. And there's an important second ingredient, provided that the operations on abstract values over 3 variables are in O of 1. So this is this part here that I have marked in red. So this is one of the ingredients that I need. Now I have so far only talked about 2 projective domains, and let's maybe get back to the octagons. And now the claim that we need for the octagon normalization to be cubic is we need to show that the octagons are indeed 2 projective. So I have here reproduced once again this formula that we have as the definition of 2 projectivity. And I will not bore you with the entire proof, but the intuition here is that one can show this to be equivalent to the Fourier-Motzkin elimination of Z from this set of inequalities. And this works over the rational, so this is sort of well known, but it also works over the integers, given that all non-zero coefficients that appear are either -1 or 1. So this means that both the integer octagons as well as the rational octagons are 2 projective. The question is, are there any other domains that are 2 projective? There's quite a few more here. I'd like to particularly point out this 2 variables per inequality domain here, because it is a bit counterintuitive why we say, okay, the normalization here somehow is not cubic, but there's this log squared factor somewhere in there. And the reason here is, in our proof, we were assuming that these operations on abstract values over 3 variables are in constant time, and this actually is not quite the case for this TDPI domain, which is why you get the complexity that we see here. Okay, so what we have thus far is we have a cubic normalization procedure for 2 projective domains. We have shown that octagons over rationals and integers are in fact 2 projective. Now let's maybe turn a little bit to how one can implement guards for 2 projective domains. Here we are restricting to these guards that can be represented exactly by adding a new constraint. For octagons, this would be adding conjunctions of octagons constraints in your guard. And what this corresponds to technically is that you have improved values in some of your clusters. So your values in some of the clusters has gotten smaller. And then, of course, you can run the algorithm that we have outlined before to restore 2 normalization, and this is going to be cubic again. However, it is known that for octagons, one can do better. One can actually do this in quadratic time. Now the question is, does this translate to the notion of these 2 projective domains? And it, in fact, does. So if we assume that some clusters have improved, here we make this additional assumption that these improvements to the clusters, you're not making them to the single variable clusters. This is just so that we can skip this initialization step. It is not a limitation, because if you want to restrict a single variable, you just add it to any of the 2 clusters that you have. But provided this is done, then one can actually run the Floyd-Warshall algorithm only for these variables that have potentially been modified. And this means that if the incremental normalization after adding constraints for m variables is then in O of m times n squared. And for the proof, we rely on the fact that you have already partially normalized the result. So basically, you have already obtained the invariant that you would obtain after the first x set minus v steps. And this already holds, so you basically only need to consider the last v steps here. So we have also quickly remarked on these guards for 2 projective domains. Then lastly, we have also considered linear assignments for octagons. Here we need to make some additional assumptions, namely we require for the sort of numeric domains that we're considering here, that if you have an assignment x equals v, x equals e, then the value for those variables that are not modified by the assignment remains the same. So if I assign to x, this does not magically change the value for some variable y. And conversely, we also assume that if I compute the value for some cluster Y that contains X, I only need to consider those variables that are either in Y or that appear on the right-hand side. So I do not need to consider all of the other variables that somehow appear. This is a sort of reasonable limitation, but there are relational domains which do not satisfy this. And given this, one can then give this new value basically cluster-wise once again. And I do this by basically meeting together all of the clusters that somehow appear. So the clusters that correspond to variables that are on the right-hand side, and these x, y that I'm considering in this cluster that I'm looking at the moment. And then if the computation on values from R over bounded set of variables is constant time, and x equals E only refers to a bounded number of variables, and R before is normalized, then the normalization of this value can be computed in linear time. Now we have this little thing to check here whether this is actually true for our octagons. And the best transformers for octagons for these linear assignments can be cast as LP problems, where one basically needs to maximize some objective functions subject to the constraints that somehow appear in the octagon, where the objective function depends on the constraint that you're considering. And the observation there, we made an additional observation, namely for closed octagons, one can somehow reduce the number of octagon combinations that need to be considered to those where the sign matches the one that appears in the assignment. This is a small improvement that we have made here. And then when we consider the best transformer for closed octagons over the rationals, then each upper bound can be determined by solving an LP problem. Solving these LP problems as polynomials. If the number of variables in the assignment is bounded, then each LP problem uses a bounded number of variables, and those LP problems can then be solved in constant time, which gives you an overall linear runtime for the case of the rationals. For the case of the integers, this is not the case. So then we have also provided some insights here on the linear assignments for octagons. So the question is, what remains there to be done? And in the future, we would like to study further these two decomposable and two projective domains. So for example, we are now considering whether one can extend them beyond numerical domains and maybe consider domains to talk about heap properties. And the other thing that still remains to be done, we have not actually implemented this yet, or we have a small prototype, but we have not implemented it in a huge code base yet. And it would be interesting to compare whether these insights that we had on these normalization procedures actually lead to any improvements to, say, the implementation in Apron or Elina, or whether the insights or whether the improvements here really are only the simplicity of the proofs. And with this, I'd like to thank you, and I look forward to any questions.
So, is there any question? Yes.
Have you thought about how you will lay out memory for when you organize your octagons in memory?
No. So this is a point that we have not considered here. So this is, and I know you're one of the co-authors of this work on these efficient normalization after adding a constraint, and I think there, in the cost model that you consider, the layout is quite crucial. Here in our cost model, we have not considered.
No, yeah, okay. So I wasn't being prickly about that. I mean, it's a sort of sobering reflection on the work that we did, is that Azim and I obsessed about the matters of complexity, and then we implemented the octagons, and we were working with quite large octagons, up to about 100 or 200 variables. And we found that the sort of dominating performance issue was cache performance. So we used cache grind on our algorithms. So like a cache miss is worth like about 100 arithmetic operations. So in one sense, we spent like months pushing at the wrong thing. Okay, we got a paper in an FMSD, but it was quite sobering in a way, in that we were sort of optimizing too early in hindsight. So I think that makes for a very interesting study within itself.
Yes, yeah, I think it's a very, very interesting question, how to get them to scale practically, yes.
Yeah.
Any other question? Right.
Well, mine is not really a question, just to point out that there is another operation that might be interesting, which is reduction for octagons, which is the inverse of closure. And this has its own uses for instance, to provide the user with a reduced output when they want to look at the computed invariants. And it can also be used to have a more efficient equality checking because they are normalization, and maybe also to define a semantic widening. So if you go on along this line of research, you might consider implementing it.
Yep, it sounds very interesting to see if one can get any results there based on this 2D composability.
All right, any more questions? Then let's thank Michael. So I guess lunch is outside, and the next session will start at 2.
Welcome back to this afternoon's session after lunch. Our first speaker is Alexandra, who's from the Mother Teresa University, so we expect a very high standard from your talk with a name like that. And Alexandra's going to talk on fault localization, so take it away.
Thank you very much. So I'll be talking about error invariance for fault localization via abstract interpretation. So fault localization aims to automatically identify the root of an error in a program by localizing it to a relatively small part or slice of a program that contains only relevant statements for the error. Here we consider so-called statement-wise slicing of the error program, where the inferred error invariance, inferred relevant statements can subsequently be changed or repaired in order to generate a correct program. In order to solve this fault localization problem, we are using here error invariance and abstract interpretation. To be more specific, we are using an iterative refinement sequence of backward-forward static analysis in order to compute error invariance, which will explain at every location of the program why a target assertion is violated. The backward analysis computes necessary preconditions at each location for violating the target assertion, and the forward analysis refines the results found by the backward analysis. If there is a precision loss when we analyze if statements, then we use their if guards, to design a BDD abstract domain on which another sequence of more refined backward-forward analysis is performed. And then the inferred error invariants are used to compute this slice of the error program that contains only relevant statements for the error. Let's see our approach through several examples. In this first example, we have a sequence of assignments and then one assertion. The assertion is obviously violated because at the assertion location, epsilon has value x plus 1. So we perform one backward static analysis, which propagates the negation of the assertion fact, x less equal epsilon, from the assertion location backwards. And in this way, at the initial location, we obtain the top element. After that, we perform forward analysis, starting with the top element at the initial location, and we propagate it forward. From the results obtained from the forward and backward analysis, we are computing the error invariance, here shown in red boxes. And they are computed in the way that we are computing the minimal sets of conjuncts from the facts found by the forward analysis that imply the fact found by the backward analysis. For example, at location 3, the conjunct epsilon equals x plus 1 implies the fact x less equal epsilon. So we keep this conjunct in the error invariant. On the other hand, the conjunct z equal x plus 1 does not contribute to this implication, so we drop it from the error invariant. Now, if you look at the error invariance, we can see that we obtain the same error invariance before and after statement at location 3. This means that no matter what statement we have at location 3, the reasons for the error, for the assertion violation stay the same. So this means that the statement at location 3 is irrelevant for the error, so we can drop it from the program slice, where we keep only the statements that are relevant for the assertion violation. So by repairing one of these two statements, we can actually make this program correct. Now we show another example with if statement. In this case, the assertion is violated when the then branch of if statement is executed. In that case, x gets value 0, so the assertion is violated. And this happens when the initial value of input variable is less than 42. So it is obviously that the statement at location 2 is relevant for the error. However, if we perform one iteration of backward-forward, if we perform backward analysis of this program, we start with the negated assertion fact, x less equal 0. Then we propagated it backwards. We obtain fact x less equal 0 at the beginning of else branch and top at the beginning of then branch. And this is propagated to top before the if statement, and this top is then propagated to the initial location of the program. So we can see that we are losing precision at the if statement. So if we perform another forward analysis, we will obtain the error invariance shown in red on the right-hand side of the slide. And from this invariance, we can conclude that both statements at location 1 and 2 are not relevant for the assertion violation, which is not correct. And this kind of imprecision we obtain because we have precision loss while analyzing if statement. So in order to obtain better precision, we are doing another iteration of backward-forward analysis, but now we are using BDD abstract domain in which the predicate B is the if guard epsilon less than 0 of the if statement. So if we generate error invariance in this case using this BDD abstract domain, in this case, we obtain more precise error invariance, which will tell us that the statement at location 2 is relevant for the error, while the statement at location 1 is still irrelevant for the error, so we can drop it from the slice for the error program. Now we show one example with while statement. So in this case, we show all error invariants that at each location show the reasons why this assertion is violated. From the error invariants, we can see that the epsilon variable is not relevant for the error for the assertion violation. So actually we can drop from the program slice all definitions of the variable epsilon. So now we can state the contributions of our works. So we define error invariants as abstract representations of the reason why the program might go wrong from some location and violate the given assertion. Then we propose iterative abstract interpretation-based algorithm to compute these error invariants. And then we have a prototype tool that is using abstract domains from the Apron and BDD Apron libraries. And we also have calls to Z3 SMT solver. And finally, we evaluate our approach on a set of C benchmarks. So the language we consider is a simple C-like sequential language that contains statement, arithmetic expressions, and Boolean expressions. we assume that a program is a sequence of statements that end with a single assertion. The concrete semantics is defined over the concrete domain of power sets of memory stores. Then we define invariance forward semantics that computes the set of possible stores reachable at any location of the program, starting from some initial set of stores E capital. And we define necessary condition backward analysis that computes the set of all possible stores from which some post-condition F capital might be reached. And this F capital set of memory stores actually contains all memory stores where the assertion, where we have, it is actually negation of the assertion fact. It represents all stores where assertion is not correct. Then we define constraint variables of a set of stores S as those variables where whose possible values are constrained in some context. For example, if we have variables x, epsilon, and z, and we have a set of stores where x and epsilon have the same values, then we say that x and epsilon are constrained variables and z is unconstrained variables. Then error invariants at each location are defined as stores from the necessary condition semantics, where we restrict the values of constrained variables such that they are contained in the invariance semantics at the same location. So for example, if we have invariance semantic at location L, which is the store x2, y2, and z3, in that case, and the necessary condition store is this one, is the one above, where x and epsilon have the same values. In that case, the error invariance will be the set of stores where x is 2, epsilon is 2, and z as unconstrained variable can have any integer. And then we show how we can use error invariance to define irrelevant statements in the program. So if we have a program P with some statement inside, and the error invariance in the location before and after the statement S are equal, in that case, this statement S is irrelevant for the error, so we can safely replace this statement with skip statement, and the resulting two programs will have the same error invariance in all locations. So the language is Turing complete, so we cannot compute the concrete semantics. So we want to use abstract semantics in order to compute invariance, necessary condition, and error invariance analysis. So we use the abstract numerical domains D such that they exist this concretization-based abstraction from concrete to abstract domain. Then we define abstract invariance and abstract necessary condition analysis that over-approximate the corresponding concrete ones. And now we show only one iteration of the backward-forward analysis for computing error invariance. So the inputs to this APS analysis are a program, the final error state, and the abstract numerical domain. Then what we do, we first perform backward static analysis to find necessary conditions at all locations. And we also find all predicates that contain if guards, where we have precision loss. Then we find the necessary condition at the initial location. If this condition is bottom, then this means that the program is correct. There is no error, so we are done. Otherwise, we are performing invariance forward analysis, and then once we find invariance at all locations, we are finding a minimal support set such that the facts from the first parameter imply the facts from the second parameter. And this minimal support set is found by via calls to Z3 SMT solver to compute unsatisfiability cores. And this procedure returns at output error invariance at all locations, the refined error state at the assertion location, and the predicate set P. And then our iterative abstract analysis for computing error invariance actually is a while loop where in each iteration we call this APS analysis using given final error state and abstract domain. If the refined error state is bottom, in that case the program is correct, so the return program slice will be only skip because there are no relevant statements for the error. Otherwise, if it's not bottom, in that case we refine the abstract domain on which we will perform the next backward-forward analysis. So now we use BDD abstract domain, where as predicates we will use the if guards generated using backward analysis. And this loop will terminate when the predicates and refined final error state stay the same over 2 iterations. At that point, we have generated error invariant, the most precise error invariance in all locations. And after that, we use this slice procedure to generate the slice of all relevant statements for the error. And this slice procedure basically checks whether the error invariants at the location before and after a given statement are the same. If they are same, then replaces the statement with skip because the statement is not relevant for the error. Otherwise, it keeps the statement. So we have implemented this procedure in OCaml. We are using the numerical abstract domains from the Apron library. And for the experiments, we use polyhedra domain. And also we use BDD abstract domains from the BDD Apron library. And we have calls also to Z3 SMT solver in order to compute minimal support sets. So we are comparing our procedure with the fault localization tool BuckAssist, which uses the CBMC bounded model checker to generate an error trace where the assertion is violated, and then this approach analyzes the corresponding trace formula using MaxSat solver. And the third approach that we are using is we use only single backward analysis to compute this error invariance. So we are using some of the benchmarks that are standard in this literature for fault localizations, like TCAS suite or some programs for CV comp suite. And for each of these three approaches, we measure the running time, the size of the resulting slice, and the precision compared to the results that would be computed if we use concrete semantics. So we can see that our approach on these benchmarks achieves better results performance-wise, precision-wise, sorry. If you look at the performances, of course, the approach that uses single backward analysis is faster, because in our approach we might have several iterations that are done in order to generate more precise results. And the performance results between our approach and back assist are comparable, except that back assist depends on the degree of unrolling the loops. So at the points where we have some while loops, its performances might degrade, because this approach might need more unrollments of the loops. So to conclude, in this work we have proposed error invariants that provide semantic arguments why certain statements are relevant or irrelevant for some error. So in a way we have provided statement-wise semantic slicing of error programs. Then we have presented an algorithm that infers error invariants, and we use them for fault localization of error programs, and we have evaluated our approach on a set of C benchmarks. Thank you.
Okay, questions from the floor?
So thank you for the talk. This is going to be a super quick question on your slide where you said the experimental results. You mentioned the performance as a percentage. I probably just missed it. Could you explain what this percentage there is?
So the percentage is we are comparing the precision of the results with respect to the results that we would obtain if we have concrete analysis.
And precision?
If we use precision 100%, it means that we have precisely identified relevant statements for the error.
So in terms of the identified
relevance,
statements.
yeah.
Okay, yep, thank you.
Okay, next question. Okay, well, if there's no question, I will ask a question. From the way you explained bug assist, and I'm completely unfamiliar with bug assist, it seemed to be doing something which is a bit like lazy abstraction and interpolation.
Bug assist?
Yeah, bug assist. So I wondered why you sort of didn't compare to like a lazy abstraction method, because the idea of computing an interpolant up to the error.
Yeah, they are using interpolants.
They are?
Yeah.
Oh, okay, fine. Thanks for clarifying that. I had no idea.
Because they create this trace formula using CBMC model checker.
Right, I see.
And then in the trace formula, they are with this max sat solver, they are kind of finding interpolants at each location.
Oh, I see. So the max is just a way of picking out these sort of relevant constraints for unsatisfiability, is it? Okay, right. Thanks for clarifying that. Any more questions? Oh, yes.
How much of the performance is, or how much of the running time is contributed by the solver calls? Is that like the thing that's bounding the performance of this tool, or is it other parts of it?
So I haven't measured here, but I don't think so that the calls to this Z3 solver takes a lot of time. I think more of the time performance is degrade when we use this BDD abstract domain, and then the whole forward and backward analysis are performed on this BDD abstract domain, and those cases have degrade of the running times.
Perhaps I can have a related question. Can you comment on how many nodes you have in your BDD domain? Because when I've done BDD work, I've noticed that the running time is very, very sensitive to the number of nodes. Yes. It can be fine, then you push it a bit and it all goes bad.
So, it's obviously that here we have tested with relatively small benchmarks. So this TKS example has a lot of ifs. So that's why at that point we obtain some bigger number here.
Right, okay.
Because in that case, maybe we can have maybe 10 if guards where we have imprecision. So at those points, we can see that the performance is degrade significantly.
Okay. Any more questions from the floor? Going, gone. Okay, let's thank our speaker again. Okay, Colin, if you'd like to set up. Okay, our next speaker is Colin Gordon, and he's going to have a follow-on talk on error localization.
All right, thank you. So, all right, I'm going to talk about error localization for a different class of analysis for this thing called sequential effect systems. I'll explain what that means exactly. This is joint work with my PhD student, Shewon, who unfortunately couldn't make the conference this year, but hopefully you'll get to meet her in the future. I'm thinking about this in the domain of effect systems, which are these extended type systems that track not just sort of input and output, shapes and operations for functions data, but also what kinds of behaviors might the program exhibit internally as it's executing. The classic example, of course, is Java's checked exceptions, right? So if you throw something in Java, and you either don't catch it and you don't declare that you're throwing it in your method annotation, you get a complaint. So that's a simple, familiar example for most people. But this goes well beyond that to things like what regions of memory are you accessing, what locked data are you potentially accessing. And these are typically modeled in the literature with joint semilattices. So some set of behaviors, and you can over-approximate by taking least upper bounds, and that gives you a partial order for subsumption. And we end up with type rules that look like this, where here I'm using these chi symbols, and I'll use that throughout to talk about some abstract behavior, some abstract effect of a program, where in general, if we think about checking, is the behavior of some unit of code, like a function or method, consistent with an annotation, we basically check, is the overall effect of this method body consistent with its signature? And then whenever we look at actual pieces of the program that have multiple subcomponents, we basically just take the least upper bound of everything that's happening there. So we take the least upper bound of the effect of computing the function term, computing the argument term, and then computing whatever computation the body of that function performs. And what's interesting here is actually, even though this theory is very nice and useful, and this is how people generally present this work, This is actually not at all how people actually implement the systems. They do something quite different. So if you were to directly implement exactly what these type rules said, you would basically just take the least upper bound of every small operation in the entire program, and then at the very end, you would do one bounds check. Is this less than the bound we wanted? So if you were doing this for Java's checked exceptions, you'd basically say, okay, we collect all the things this method body might throw into some set X, and then we check at the very end, is this less than the throws clause? If we say throws Y, is it less than Y? This, of course, yields pretty useless error messages. And the reason for that is because if you can imagine you have something like 700 lines of code, somewhere in there you throw a particular exception that is not supposed to be thrown according to the throws clause. If you get an error message that's basically, well, if we collect all of the set of exceptions thrown anywhere in this 700 lines of code, this is not a subset of what you said it threw, it doesn't really help you find the source of the error, right? In this particular example, you could grep for throws and find it, but if that was hidden behind calling another method, it would be significantly harder to debug. Because there's no information in this coarse-grained comparison about where the error lies. So what people do instead is what I'll characterize as local. So they figure out an equivalent way of checking the same rules, but with a bunch of many, many local checks instead of one global check. And the intuition here is, of course, that they basically check for every individual action of the program and every method that it calls, is that individual program component's effect less than the bound. So if we have some function like this that says, okay, well, we're allowed to throw exceptions A, B, and C, and it goes through and says, okay, does A throw something in ABC? If we assume A throws A and B throws B, this goes on, and it's fine. It can check, okay, A throws A, that's in the set, great. B throws B, that's in the set, great. And this lets us get good error messages, because if it gets to D and D throws some exception D that's not in this set, it can say, well, it's this call that's the problem. It's not vaguely somewhere in the method. And this works because of this property of joint semilattices, which is this universal property, right? That in order for some join of some large set to be less than a bound, every individual thing in the set has to be less than the bound on its own, right? And so there's this nice algebraic connection between this global view that's very convenient for working out theory and designing analyses, and this local implementation that gives much better error messages. So we're interested in doing this for a slightly broader class of effect systems called sequential effect systems. You might have heard these also called flow-sensitive effect systems. The terminology started kind of fluctuating about 10 years ago. So Java's checked exceptions, of course, are not flow-sensitive. If you throw A and then maybe throw B, or throw B and then maybe throw A, it's the same effect. It's the same set of possible exceptions thrown. But if you want to start talking about some behaviors over time, like are you acquiring a lock and then releasing it, or are you releasing and then acquiring? Because those are not the same behavior. They're not interchangeable. Or if you want to worry about the order of security-sensitive operations, are you checking for authorization before you release data publicly instead of the other way around? We want to be able to reason about that. Or more broadly, many of these can be characterized in terms of sets of finite traces, which turn out to also form an effect system in certain models. So the literature here is a little more varied than for traditional effect systems. Traditionally, it's, like I said, almost always a joint semilattice. There's a lot more proposals in play for sequential effect systems. I wrote a paper a few years ago that has a survey if you want to see the full menagerie. But we're going to use this particular model I proposed, not just because I proposed it, but for technical reasons you'll see in a second, where it's called an effect quantale. And the idea is we have a structure on the set of effects E that has not just a least upper bound. So we still have a joint semilattice in there. We still need to be able to over-approximate, well, we don't know which branch of the conditional we're taking, over-approximate both. But we also have a monoidal structure in there for sequencing. So this sort of right triangle symbol we say is sequencing. And so if we have A sequence B, it means we're reflecting the fact that the behaviors in A happen before the behaviors in B. They precede it in evaluation order. There's some additional conditions in there. You'll notice the word partial here. Here and other parts of the talk, if you want to tune out the word partial, you can. There's one place later where it's important, and I'll point that out. And there's some laws for how these interact, so sequencing distributes over join, and we have other nice algebraic properties there. The real reason this is useful for us with an eye towards building real tools, though, is because there's also been work on using, from this structure, you can derive iteration operators to deal with loops, to deal with fixed points, and also support for non-local control like early returns, exceptions, and other things that happen in real languages. Also, as a special case, it captures the traditional regular effect systems as well. If sequencing is just also join, then it happens to also be commutative, and you get all the same results you would care about. In this setting, the type rules shift then a little bit to take advantage of these rules. So this is the rule for calling a function in a sequential effect system. We've switched from taking joins of everything to actually reflecting the behavior of the function happens before the behavior of reducing the argument before you actually invoke the code, since that's the evaluation order for left to right call by value. There's also a little shift in when we allocate a function. Instead of it being the bottom behavior, it's actually the unit for sequencing, right? Because unless you're in the narrow domain of reasoning about memory allocations of closures, it's generally not an effect we care about, but it's otherwise similar. So what we'd like to do for this richer model of program behaviors is figure out how do we implement these and get good error reporting. So in prior work, there's basically two approaches people have taken. One is sort of what I said was the bad approach for traditional effect systems, and it's still bad if you do this for these sequential effect systems, and that's you just compute with all of these operators based on the type rules, a big expression with sequencing and joins, and then you compare it once at the end to some annotated bound on behavior. And you get bad error messages with this for the same reason as before, except maybe even worse because the algebra is a little bit harder to think through. The other alternative, the other thing people have done is they've used type inference, right? So basically generate a bunch of constraints based on what it would take for a program to be type correct and effect correct. And then these get handed off to a constraint solver that works through them in some convenient order to reach a conclusion. And this is better, and it will give you local errors, but it also is a little bit unpredictable in the sense that if you just hand this off, in general, when you do constraint solving, you don't know what order the constraints will be solved in. If a constraint ends up being violated, it may or may not be an actual constraint related to a mistake, or it may be that your mistake propagated some weird information to a distant, unrelated constraint. So sometimes you get good error messages, and sometimes you get weird error messages. And there's lots of general work in this space of how do you improve error reporting for type inference in general. It's still a little unpredictable, but it's still lively. There's cool stuff happening. There's a paper later this week at Uppsala I'm excited about. But for this domain, it doesn't solve the problem. We don't get precise error messages. So what we really need, we need something like what we have for the joint semilattice case, where we have some algebraic shift from looking at things as a global check over the behavior of all the code in the method against some bound, to some local checks that we can use to give more error-precise reporting. So what we're trying to do is come up with a way to relate a local and global view, and historically, there has been no local view for these flow-sensitive effect systems. So the key ingredient turns out to be this idea that has a rich history in the mathematics literature called residuated semigroups. So I'll preface this by saying I'm going to ignore a couple subtleties that turn out to be important for actually building a tool and making this work for the full effect quantales theory. But the presentation in the paper is a direct refinement of this, so this is the core key idea. And I'll also note that there's a subtlety that's easy to overlook, which is that while this solution applies, we can define what I'm going to talk about for most effect quantales, and certainly all of the effect systems I'm aware of in the literature. It doesn't follow from the axioms for an effect system that I'm working with. So it is possible, though we're unaware of any counterexamples, it's possible there are some effect systems this won't work for, but we haven't found any yet. So the core idea is this idea from mathematics called a right residuated semigroup, right? And so that's a bit of a mouthful. And the idea is basically you take a partially ordered semigroup which you'll notice that I'm consciously using notation that's basically the same as the effect quantile notation because they're basically ordered semigroups. And there's this one new operation, this backslash, which is partial. So it's partially defined. So this is the one that's important to know is partial. And when it's defined, it has this interesting property. So if we are, say, checking a method body and we are looking at the relationship between some prefix of method execution, characterized here by y, and some rest of the method body x, and we want to compare this to some upper bound like a throws clause z. On the right here, we have basically the global characterization of, well, we have these two expressions, they're executed in order, we sequence them and compare them to the bound. And then on the left, we get this different relationship. So this slash operator, this y/z, is basically if your ultimate goal is behaviors characterized by z, what's left if so far you've done y? And so this constraint says that basically if we want y followed by x to be less than some bound, in order for that to be true, x just by itself has to be less than whatever you have left after executing y. So I know this is still a little bit abstract, and we'll get into details very, very quickly. But there's a couple, just general note, if you fill in some of these details that deal with a couple extra quirks of effect quantiles, this core idea carries over to effect quantiles, and that's sort of the key technical development in the paper. So I know this is still very abstract. The key thing to retain from this slide is y/z is what's left to do in z, if z is the final goal, after you've done y so far. So as you're going through execution of a method, if the things you've looked at so far have behavior y, and your final goal is z, this residual is what's left. Right? What are you still allowed to do? And this gives us the local view of checking that we actually need to give localized error reports. So if we're just doing two expressions in order, we're not doing application now, it's just we're running one expression, then another, they just happen to be evaluated in some order, and their effects are chi1 and chi2. If we take that law from the previous slide and push this forward, then in order for sequencing those things to be less than some method bound, then it has to be the case that if you take that method bound and take the residual with the first expression's behavior, that still has to be greater than the second expression's behavior. So this now has shifted us from a bound on the larger expression to a bound on just the second expression's effect by itself. And this is actually important because there's two things going on here. There's two important constraints. One is that this residual has to be defined. So it's possible for this to not be the case. For example, if you've already done too much, right? So if we did take this with the special case of treating traditional effect systems like this, as if they were sequential, if it says, you know, you're allowed to throw A, B, and C, and you've already thrown Q, you're out, right? The residual will be undefined because there's nothing you can do to sort of take back that Q later. The other thing is that it also gives us this upper bound on what's left. So if the type checking algorithm examines things in sort of top-down, line-by-line program order, at some point we have an effect for a certain amount of the code in the method, and we can use that and the upper bound to give a tighter bound on the rest of the method that hasn't been checked yet. So this ends up being, in a recursive type checking algorithm, we take this upper bound and we continue taking residual and residual as we visit more and more and more lines of code. And this basically narrows down possible behaviors for the rest of the function as well. So if we have a program fragment that just does two operations, like call B, call C, if we're doing this with finite trace effects, where these are some maybe security sensitive operations, we want to see, are we following a certain prescribed protocol of doing these things in order? If the target bound, the things we're supposed to do are first you do A, then you do C. This is enough for us to flag B as the problem rather than just saying the whole method is wrong, because the residual of AC minus B is going to be just undefined, right? If you're supposed to do A and then do C, but you've done something unrelated instead, there's nothing you can do later to get back to having done A and then C with nothing beforehand. You've already kind of done too much. So that's the key idea, and the paper goes on and develops this with a little more nuance and dealing with some of those additional subtleties I said I was sweeping under the rug for a type lambda calculus. Describes the type checking algorithm in detail, proves the checking algorithm is correct and sound for a type lambda calculus, and in particular that it gives the earliest statement in program execution order at which it's clear that you've already made a mistake. And we'll see an example in a slide or two. It describes a full implementation of this for Java, building on some of those constructions I mentioned for effect quantales earlier, so that's online. And then it shows examples, like we'll look at in a moment, of doing this for a couple concrete sequential effect systems. So one of the, sort of from a historical standpoint, earliest like well-known flow-sensitive effect system is this system from Flanagan and Kadir from 2003 that deals with atomicity. So in a concurrent program, you might call a block of code atomic if its execution is indistinguishable from, if other threads cannot tell the difference between that unit of code executing all as one with no interruption or interleaved with actions of other threads. And so the idea, I won't get too far into the details, it's built on this theory of movers from Richard Lipton in the 70s, but the idea is basically every action in the program gets labeled with how it would commute with respect to actions of other threads. So there are actions that commute both directions, like you assigned a local variable. And there are actions that commute only one direction, either only later, like acquiring a lock, or only earlier, like releasing a lock. And if you can sort of commute all of these things together into one big block, you can say it's atomic. That's the idea that's trying to be captured by this sequencing operation here. So they implemented this for Java back in 2003, and they found a bunch of atomicity bugs in Java 1.4. So one of the secondary reasons this paper was important is because it was one of the earliest papers on this class of concurrency bugs as well. But there's actually no information in the paper about what error reports look like, and kind of reading between the lines, it seems that they basically did bottom-up, which is the direct thing to do if you have sequencing and composition and least upper bounds. But, all right, where'd that go? It's still down here. All right, well, I'll say a few words more, but there's another slide that actually has concrete example of checking this for a Java program. Long story short, we've implemented this for Java, as I mentioned a second ago, and with a little bit of deep Googling, we managed to find the JDK 1.4 sources. And with a little creative massaging, we managed to actually run our modern tool on the JDK 1.4 sources, which actually took some work, but was not actually as bad as I was afraid. And then basically, among other things, so we ran this on some new examples as well, but we also re-implemented this system I was just talking about for Java in this modern framework and ran it on this old JDK 1.4 code to see what happens when we tried to give error reports for these known bugs. So the results, as you might guess from the fact that the paper was published, were good. You may have to use your imagination with the penultimate slide of my talk, which was actually the code example. Aha, okay, thank you. Yeah, so here's an example. This is code from JDK 1.4. So that annotation, that @atomic at the top, is actually an annotation from us using our tool, marking that this method is supposed to be atomic. This is one of the bugs they found was this method actually in JDK 1.4 was not atomic. And the reason for that is line 1, it calls length on a string buffer. And line 4, it calls get value on a string buffer, but there's no synchronization. So in between those two lines of code, some other code might be able to modify the value of the string buffer and change the length, right? And so simplifying slightly, what our tool ends up noticing is that the effect of these first 4 lines is effectively non-atomic, which is the greatest element in the ordering on effects. And then every time it goes through a line of code, it checks, okay, is the residual of our current bound with this code we just checked the effect for still defined? And if it is, it pushes that down further. And so simplifying slightly so you're not staring at a residual of a residual of a residual of a residual, essentially what it notices is, well, the residual of atomic with respect to non-atomic. So what's left if you are trying to be atomic in behavior, but you've already done things that are not atomic? Well, that's undefined. And so it notices that on line 4, and so that's where we report the error, which is exactly, that's the earliest line of code in this example, where once you've done that, you've already broken this guarantee. It's already too late, you're non-atomic anymore. Doesn't matter what else is left in the code. And so this gives us a much more precise error location than just saying, well, it's somewhere in this line of code, right? Which for this method is not terrible because it's not too huge, but for larger code and certainly for more complex effect systems, it gets quite tricky, right? So wrapping up, the things we did in this paper are identifying this algebraic relationship between this sort of local and global views of traditional effect systems and how this sort of connects theory and practice, and finding a way to extend this to at least some flow-sensitive effect systems. We implemented it for Java. It's online. There's an artifact linked from the paper. And we validated this on some existing and new effect systems. So, thanks.
Okay, questions from the floor? Right at the back.
Thanks for your talk. So my question is, there might be multiple same effects in the global constraint. So how do you know if you have a local constraint saying X follows Y, then how do you know which Y it's the one you want in the global constraint?
Yeah, so that's a good question. So for that simple example that I showed a few slides ago, you know, there was only one trace. Like it was definitely, you wanted to do A and then C, and that was it. Just to keep the example simple. But this theory works out even if your traces are sets of traces, because it turns out actually not just formal languages, but even regular languages, you can define this residual operation. That's also in the paper.
Okay, thank you.
Yeah. Okay, any more questions? Okay, well, if there are no questions, I will ask a question. Your intriguing residuated semigroup /
yes
operator, that seemed to be a bit like an abductive
yes
operator, and it sort of reminded me of that work that Roberto did. I guess he's in the audience somewhere. When he had this, when he and his colleagues had this domain refinement technique, when you took an abstract domain and you added, you performed height enclosure, was it? I remembered. Okay, and that gave you this arrow which allowed you to do a form of abductive reasoning. So there seems to be, that seems to resonate.
That certainly sounds related. I'll have to look at that in more detail. It sounds cool.
Okay, any other comments or observations from the floor? Well, if not, we will thank our speaker, and perhaps the next speaker could set up. I think we all think that Colin did very well, punting while the sort of technical things were being solved. So well done on doing that, Colin. Okay, so our next talk is by Anastasia, and we're moving on from fault localization to reasoning about round-off errors, but also round-off errors in the large, which is a very tricky problem. So it sounds like a very intriguing talk. So when you're ready, Anastasia, take take it away. This is joint work with Eva, who's also in the audience.
Okay, thank you for the introduction. So today I'm going to tell you how to scale up rounding error analysis for loops over data structures. Now, when we implement real-valued algorithms in finite precision, we inevitably introduce rounding errors, and especially for safety-critical software, we want to make sure that these errors are bounded and compute a sound worst-case upper bound for these errors. For instance, we can compute an absolute error bound that would quantify the difference between what finite precision computation computes for us and what is the ideal expected result of this computation across the input domain. For instance, for such a straight line code, we can use one of the state-of-the-art tools to compute the absolute error bound and the real valued range of the value of the resulting value in a matter of seconds. So for small straight line code, there are plenty of tools that can compute tight error bounds for both linear and nonlinear arithmetic. However, scalability of such methods is still work in progress. And among other things, loops are presenting a different challenge that is probably best illustrated with an example. Say you have a loop that sums up 100 elements in the range between 0 and 100. And to the right, we depict the dynamically sampled rounding error for this loop across different iterations. So as you can see, the error varies a lot across different iterations. And generally, there is no obvious correlation among the number of iterations and the magnitude of the error. So what we can do with that, we can try to reduce the analysis of loops to analysis of straight line code. And for bounded loops, in particular, if we can statically reduce the number of iterations, we can perform unrolling, which works well for small loops. But again, if you have large loops, then such an approach does not scale. An alternative would be to find an abstraction of a loop. Again, finding an effective abstraction is actually challenging because standard static analysis approaches, such as applying a widening operator, does not work well for rounding error analysis because it often returns trivial error bounds. And other methods that actually do deliver more precise error bounds require additional input from users. For instance, finite precision inductive invariant, which by itself is already challenging to compute. So a key idea of our approach is to use a functional way of specifying our loops. And in particular, we focus on loops over data structures, such as vectors and matrices. And the benefit of specifying the algorithms in functional way is twofold. First, we allow a user a concise way of specifying the algorithm, and also we can benefit the analysis because, say, if we are given a map over some vector, already at syntactic level, we know that there is no data propagating across different iterations of this map. And in order to use this information, we also defined an abstraction over data structures that ideally will allow us to avoid duplicate computations in the analysis and scale up. So now let's have a look at the example. Say you want to compute a heat distribution over some one-dimensional line, and you are given a set of points with initial values for the temperature. And say you want to compute the temperature after n time units in the middle of this line. So what you have to account for is that neighboring points affect the temperature of each point. So you have to compute it for each point at each time unit repeatedly until you reach this desired number of time units and your central point. How do you implement such an algorithm? So you can use an imperative style loop, which works fine, but you have to use two nested loops, with rather non-trivial loop exit conditions, so maybe error-prone. And moreover, if you want to use state-of-the-art tools that can actually analyze, report rounding error bounds, more likely you would also have to unroll this loop and obtain over 1,000 lines of code. So what we propose to do instead is to write it in a functional style. And then you end up with just 6 lines of code, and there are no explicit indices in this algorithm, so it is potentially less error-prone. And let me jump a little bit ahead. If we analyze such a program in a functional style, we are reporting error bounds of roughly the same error of magnitude of errors compared to imperative and unrolled loops, but we can do that much faster. So let's rewind and let me tell you how we actually got there. So we determined that in order to implement this analysis, we need 3 major components. First, the functional domain-specific language that operates over data structures, then an abstraction of these data structures, and transfer functions that actually operate on these abstractions. Let's start with the first one. So following previous work, we determined that our DSL should have real-valued semantics. First, it provides a clear reference semantics for arithmetic operations, and it is also more intuitive for users to write in real-valued. In such a way, we can just provide a finite precision as a parameter to the analyzer and analyze rounding error for a particular precision. Now, if we want to analyze loops that traverse a data structure, we need to know their size. And in our domain-specific language, we propose to specify the maximum size of a data structure because results of the smaller size data structures will be subsumed by our analysis results. And last but not least, as for any rounding error analysis, you need to know ranges of values. For instance, we can specify that all elements in our input vector AX are in the range between 1 and 2, or we can also be more precise and say that there is a subset of elements that has a different range. In this particular example, it's a smaller range, but can actually be anything. Now, what is left to do is to determine operations that actually implement the algorithm. And here, it's just to give you an idea of the size of our DSL. So the design of the language itself was guided by practical applications that we found in open source projects of different domains. And we can roughly split it into 4 different groups of operations. So our DSL supports standard higher order functions, such as map, fold, and filter. And also there are variations with an explicit loop counter. Element-wise arithmetic operations that perform operations on the elements with the same index of the input data structures. Domain-specific functions, for instance, matrix multiplication that is needed to implement neural networks, and also non-numerical operations, such as appending an element or adding a padding around the matrix or a vector. For instance, using our domain-specific language, one can implement a layer of a neural network like this, where we multiply a matrix of weights with an input vector, then we add a vector of bias, and then we implement the rectifier linear unit using a functional map and a maximum over an element of a data structure and 0. So the next component that we need for our analysis is an abstraction of data structures. Again, let's go back to our simpler example with the map. Say you know that there is no propagation of values happening across the iterations, but if you don't have any useful information about the input vector itself, then what you're left with is state-of-the-art, just unroll and compute for every element separately. Now, what we propose to do instead is to group the elements by ranges. For instance, if we know that all of the green elements are in the range between 0 and 1, and all of the orange elements are between 2.5 and 4, and we know that there is no propagation of values across iterations, it is sufficient to compute once per group of each color. So we've introduced our data structure abstraction to group elements by range, where each group is represented using a set of indices. So here n stands for dimension. It would be 1 for vectors, and it would be a tuple of indices for matrices. So indices inside one set do not need to be consecutive, but they have to be unique and valid indices of a data structure elements. So in different sets inside one abstraction must be disjoint, and a union of all sets should cover all possible elements of this data structure. Since our analysis tracks values of variables and also errors on them, the abstraction also accounts for tuples of the ranges. And we can get these abstractions either from input specification for input data structures or from some transfer functions that generate fresh data structures inside our algorithm. Again, let's return to our example with the heat. And here from the input specification, we see that the input vector has the size 33. So valid indices will be in the range between 0 and 32. We also know that the elements with indices from 1 to 4 have this special small range, and all other elements will be in a different group with a range from 1 to 2. Inside our algorithm, we are also introducing a new vector. And notice that the first and the last elements of this vector have the same range. Well, actually, it's a constant, but it's a point range. And the middle element will be put in a separate group with the only index 1. We also have the same abstraction for errors. I'm just not showing it on the slide to make it a little bit more concise. OK, so now that we have our functional DSL and the data structures, we can combine them together and actually design the analysis. The general idea is to analyze as rarely as possible, so potentially analyze only once per each unique range of inputs. In a way, you can say that we are reducing the analysis of loops to analysis of straight line code. And unlike the typical unrolling, we are only doing it once per group. So you can say it's a piece-by-piece unrolling. And once we unrolled, and also for scalar operations that appear in the algorithm, we apply existing baseline data flow analysis as it is implemented in tools like DAISY and Fluctuate. So in this work, we focus on IEEE floating points, but our approach is directly applicable to other finite precisions as well. Now, depending on the exact semantics of each operation, different operations will benefit differently from our approach. Let me walk you through that. The simplest case is non-numerical operations, because they by themselves do not commit any error, but they do affect an abstraction. For instance, if we want to add a padding around some matrix A, for which all elements were in the same range, we need to shift the indices in the column and in the row by 1, and also add an additional group of elements that accounts for the first and the last row in the column with the range 0. Operations that benefit the most from this once per range analysis are arithmetic operations. In particular, unary operations can be, because there is only one input, we can apply directly only once per range evaluation. And it would work for unary minus, square root, transcendental functions, and also a map, because it's also a unary function, just a user-defined. A special case of a unary function that also benefits from this once per range evaluation is a filter. Because it contains conditionals inside the definition, we want to avoid creating additional rounding errors, and we restrict the analysis only to predicates of a simple form where we compare a variable to a constant. Another thing that makes filter so special is that it's the only operator for which concrete semantics are not exactly mirrored in abstract world. In the concrete world, a filter would create two disjoint sets, one that satisfies a predicate and one that doesn't, and only take the set of elements that satisfies the predicate. But in the abstract semantics, those sets are not necessarily disjoint, so we have to account for that. And in order to stay sound, we over-approximate the resulting data structure and take all groups of elements that may potentially satisfy this predicate. So for binary operations, we are using the same approach, the same idea, except now we have two operands and not one, so we have to account not for one unique range, but for a unique pair of ranges as an input to an operation. So say if you have vectors A and B, and you want to perform an element-wise sum, you will create 4 different groups where you combine green elements with green elements, orange with orange, and green with orange, and orange with green. And for matrix multiplication, the idea is exactly the same, except you would have to align elements not by their index, but it would be a left-hand side row and the right-hand side column of the matrix. And the expression for actually evaluating the resulting element will be constructed internally by our tool. Naturally, not all of the operations can benefit from simple grouping of elements. So, for instance, if we have a value that is recomputed at every iteration and then propagated, such as an accumulator in faults or an explicit index in the enumerators, then we cannot directly apply this approach. Then, in this case, the analysis falls back to the default behavior and unrolls the loop. However, we noticed that for many of the faults, the structure of this higher order function that is passed to the fault is actually relatively simple. So we can optimize and still make use of this once per range evaluation if we over-approximate the value of the accumulator. And we identified 2 cases when this is possible to do: a general linear expression and a particular case, a special case of the linear expression as sum. So for the sum, it's probably the simplest case because we determined that our domain-specific language has real-valued semantics. The sum in real-valued arithmetic is both commutative and associative, so we can rearrange the elements however we like. Therefore, for each group, we compute the sum with the number, with this simple closed-form formula, and then we unroll the error computation using this over-approximated accumulators range. For a general form linear loop, it's slightly more complex because here the resulting value depends on the order of computations. So we first do some pre-processing and we split and sort the groups of elements such that each group only contains consecutive elements and they are sorted starting from the element with the index 0. And then we apply the same approach. We over-approximate the accumulator using this closed form formula, and we unroll the error computations because there is no simple closed form formula for the errors. Now, we implemented all of these necessary components in a tool called DSTool and evaluated it on the new benchmark set. So since we are the first ones to explicitly target analysis of loops over data structures, there was no standardized benchmark set. So we collected the benchmarks from open source projects in different domains and repurposed some from related work. In our evaluation, we wanted to answer 2 questions. How does DSTool compare to state-of-the-art tools, especially in its scalability? and how does an abstraction affect results of our analysis. In order to do that, we determined our benchmarks to have between 10,000 and 700,000 iterations, where each iteration would have between 1 and 1,000 arithmetic operations. We also played around with the granularity of specifications for input data structures and varied them from very coarse ones, where all of the elements inside one data structure would just get one input range assigned, to very fine-grained, where each of the elements would get a unique range and two configurations in between. We compare our tool with two state-of-the-art tools. Fluctuat, in particular, can handle loops without any pre-processing, but only in imperative-style loops. And its baseline analysis is also remarkably effective, so it is more scalable than competitor tools. And among those tools that can only handle straight-line code, Satire was also shown to be the most scalable. And precisely, we will compare two metrics: accuracy in terms of rounding error bounds and performance in terms of analysis time. So when answering the first question, we wanted to know how many benchmarks tools can handle. So we determined that a tool can handle a benchmark if it reports a non-trivial error bound within 30 minutes. And results of our experiments indicate that DS-tool was able to handle many more large benchmarks compared to Fluctuat and Satire. Whenever Fluctuat and Satire did report some values, we also compared their relative performance by normalizing the analysis time of Fluctuat and Satire over DS-tool's analysis time, and noticed that the DS-tool was median 24 times faster than Fluctuat and 260 times faster than Satire, and also it was at least 9 times faster than Satire on large benchmarks. We also compared relative accuracy, and here I should also note that we ran DS-tool with this over-approximated evaluation of faults. So predictably, the accuracy of DS-tool was lower than for other tools, but it is still of the same order of magnitude. So we conclude that DS-tool scales better to large programs because it handles more large benchmarks, computes the results faster without significant accuracy loss. In order to evaluate the effect of the data structure abstraction on our analysis, we compared the DS-tool with an abstraction, but without optimization for faults, to simple unrolled versions of the analysis. And again, we compare relative performance and accuracy. So here, I'm showing you results for the coarsest specification, and for other specifications for inputs of data structures, you can look it up in the paper if you want. So what we noticed is that relative accuracy for all benchmarks was exactly 1. Those are the points that are plotted along the horizontal axis. So it says that our abstraction alone does not have any effect on the accuracy, but it can improve performance, and in the best cases, this is by a factor over 700. So another thing that we wanted to evaluate is how our optimized faults compare to the traditional unrolling scenario. And here again, we are comparing relative performance and relative accuracy. And let me show you a particular example. So this dot stands here for a benchmark that computes an average over 10,000 elements. And this is a specification where all elements have the same range. And using our optimized fault evaluation, we were able to compute results 31 times faster than with just unrolling, and only by a factor of 2.3 less accurate. So you can also navigate these effects by specifying by providing more fine-grained specifications. For instance, for the same benchmarks with the 10,000 elements, but with 1,000 unique range specifications, we can reduce the factor of accuracy loss, but also we are losing some of the performance. So we conclude that our fault optimization provides a viable trade-off between accuracy and performance, and we can also further navigate it by providing different granularity of input specifications. So as a takeaway, I would like you to remember that scalable analysis of loops is still challenging, but we can improve the scalability by using semantic information from functional style specifications. And in particular, we achieve the scaling up by coupling an abstraction of data structures and analyzing only as rarely as possible. Our tool showed that we can handle more benchmarks and do that faster than the competitor tools without a significant accuracy loss. We implemented everything open source, and it is a part of the framework DAISY. So it is available on GitHub and also as an artifact linked in the paper. Thank you for your attention, and I'm happy to take questions.
Okay, questions from the floor. Oh, right at the back.
Let me see. Maybe I missed something, but I think you mentioned when you talk about the fold, you mentioned commutative and associative, but you also mentioned IEEE 754, which.
Right. So there is a difference because the semantics of the DSL itself is real valued.
Okay.
So we are computing sort of against this real valued specification, and then for the order for which we will compute with this real valued specification, if you implement exact that order with floating points, the error bound holds. So our tool actually can generate the code for that. So for the code that is generated by DS2, the bounds will hold.
Okay, that makes sense. That's
Yeah,
what I
yeah,
was
yeah,
thinking,
that's
but I
an
just
important
wanted to
point.
clarify because I was like, that's
Yeah,
they don't quite match.
That is
Thank
true.
you, thank
That
you.
is true.
Okay, any more questions? Yeah.
Thank you for your talk. Can you deal with infinite loops?
No. So this approach only works on bounded loops. You need some kind of different way to abstract it, because if your group is infinite, well, okay, that depends. I think if you have like an infinite data structure, but you apply a map, I mean, that would.
No, but
kind
in
of
your
still
benchmark,
work.
you talked about filters, and these filters can work forever, and you can infer bounds on these errors.
Right, I guess we use the filters on the bounded data structures, but yeah, if you want to have this kind of infinite filter, then you would need some different, like you need some way to abstract a loop then in a different way.
Okay, any more questions? Oh, yes.
Hello, thank you. About the accumulator, so what you do is you group the elements and you abstract those groups. But I'm not sure to understand how you choose those groups and what are the criteria you use to.
Just a range of values. I mean, this can be. So if you specify inside your for each input data structure, you have to specify what is the range. And there, that's the case where you can regulate it. So if you say you have all of the elements inside your data structure have the same range, I don't know, from 1 to 2.
Okay, but
that's how you know you only have one group. So if you modify it further, say, I don't know, you take a subset of the values and then you multiply it and then concatenate data structures again, then you will get a resulting data structure that will have several groups, right? So it is like each transfer function will affect that. But I think I would have to like walk you through examples. I don't know how general I can answer that question.
Okay, but if you have, so at first you have an array, for example, that has multiple values. and you need to construct those pools of intervals, for example.
That's just provided by the user.
Okay, okay. So this is a fixed amount, fixed number of pools. That's it?
Yes, yes, yes.
Okay,
so
thank you very much.
unless it is modified inside the algorithm, it will be fixed.
Okay, thank you.
The questions keep coming.
No one wants a coffee break.
It's pretty cool work. So I'm curious how far off do you think this would be from extending it to support unbounded, still finite, but unbounded, like not statically bounded structures?
Can you give an example of such a structure? I'm just struggling to...
I mean, maybe I'm reading more into your examples than you intended, but so for example, you give this example where we know the size of the array is 33. What if we don't know the size of the array? We just know it's finite because it's an array.
Right.
But we might know some information about maybe it has some bound n and the first half and the second half.
Well, I think generally it is a difficult problem for rounding error analysis because, like, if you just take a general case of a loop, the error is unbounded. So you need to know some kind of upper bound on the number of iterations with which you can then compute a precise value. But again, so because we only require you to have a maximum number of, like, maximum size of the data structure, then you can over-approximate.
Okay, any final takers for the final question? If not, let's thank our speaker again. Okay, so it's some time for tea, but at 4 o'clock we're back again for a keynote. Isn't that right, Manuel? So don't miss that. See you at 4.
Yeah, there you go. And now. We have the slides. Can you hear us? No? He doesn't hear. Can you hear us now? Hello, can you hear us now, Gangdeep? He doesn't hear us. Can you tell him to check his? Okay. And his sound maybe? Can you tell him to? His speaker maybe not up. Oh, we're muted, no? No, he's muted. He's muted. Hello, Gagandep, can you hear us?
Yes, I can hear you.
Oh, now, finally. Yes, you were muted, so we didn't understand. All right.
Oh.
We're so glad to see you and to see your slides. All right, Gagandep, sorry about the mishap. It seems like everything is fine now. So it's a real pleasure to introduce Gagandep. He's going to give us a keynote on building trust and safety in artificial intelligence with abstract interpretation. He's a professor at the computer science department in the University of Illinois, Urbana-Champaign. He has been working at the intersection of machine learning, formal methods, and systems for quite a while, and he's going to talk to us precisely about this topic. So we look forward to your talk, Gagandep. The floor is yours.
Thanks for the introduction. I'm delighted to be giving this keynote at SAS. So this is a joint work with a lot of collaborators at UIUC, VMware, Stanford, and so on. I can hear some echo somehow. Okay, so I don't have to be precise that the deep learning revolution is going on. For example, from my perspective, in the last few years, some of the things that have captured public imagination seem to be coming from deep learning. The latest example is ChatGPT. I talked with somebody on the train. They know about it, right? So these kind of solutions are capturing public imagination. Now there are issues with it. So the first issue is
Are the mics muted?
adversarial attacks which have to be known. It can be done in many domains, many of these deep neural networks. A guide for manipulating 24 election, it will not give you the answer, but you can add some special kind of text to the end, and then it will start giving you all kinds of
toxic outputs that you want. So these have been demonstrated on state-of-the-art models as well. This is just an example for large language models. I wanted to show it because it's the latest technology, but we have been studying this kind of adversarial attacks on the vision domain and other domains for the last 5-6 years. What is the other problem? The other problem in general is out of distribution generalization. So when people say about human level intelligence, uh, what you want is that we should be this model should be able to match the performance of a human. Now in the vision domain particularly, this is currently not the case, even with all the progress in the last 10-11 years. What you want is if you train um, on some training data, then you should be able to generalize on inputs that are not in your training distribution. So for example, if I have trained a classifier uh, on ImageNet data, then even if I add different kinds of noises, for example, snow, frost, fog, uh, blurring, and so on, a human would be able to still recognize the object, but these deep learning models do not seem to be that robust. So auto generalization is a very important problem, and for me, it's very necessary to have this kind of properties if we want to talk about real world deployment. Now, the third problem is these deep learning models, they are constructed in a black box manner from data. So we train it, they are highly nonlinear, they get good performance, but we don't know how they behave. So there's a lot of work on interpreting how these models are working. So that involves finding out what parts of the input. This is one of the most common way of interpreting deep neural networks is to find out what part of the input is the network focusing on to make decisions. Uh, in many cases, what you find is that even though the prediction is correct, the model itself might be looking at some nonsensical part of the input. Basically, this is called like a spurious correlation. So the model during training, its only goal is to maximize performance on test set accuracy. Now there are maybe thousands of ways of doing it, and model sometimes just learns to just maximize this accuracy for getting by relying on some spurious correlation. Now, I believe that if you just train the model to maximize accuracy on test set, it's not that suitable for real world deployment. For example, if I want to go from place A to place B as fast as I can just drive in a straight line very fast and maybe kill all the pedestrians or have a lot of crashes. Well, that's not safe, right? So this is also the case with deep learning, in my opinion, is that you want to have high accuracy, but you also want to have some kind of human aligned properties. And this is where I believe abstract interpretation or formal methods can work. So I do believe that this is how the pipeline, when we are looking into designing models for real world deployment, should look like. So first, of course, you should collect data, and then you should train a network DNN to get high performance on that. Once you have done that, you should not only think about its accuracy, but you should also think about whether the model is trustworthy. Now, trustworthy is a very subjective term. It's also a very broad area. There are many notions of trustworthiness, uh, and it is very domain dependent. So in that case, I would say that the developers who are developing these DNNs for real world scenarios need to define what do they consider trustworthy behavior and formalize these properties. Once they have formalized what do they expect for the model to be trusted, they should try to verify that, and that is where abstract interpretation comes in. And then they should check whether the model has the desired degree of trustworthiness, and I will discuss what do I mean by this desired degree of trustworthiness. Um, if it is not, then they should retrain the model to be trustworthy and accurate and fast. So this is like a three-way trade-off that needs to be balanced to get real-world deployable models. Uh, Once you have ascertained that the model is fast, accurate, and trustworthy, you can deploy it, but usually still people do watch out for distribution shifts. So you may have to retrain or repair the model again and again. So in this whole pipeline, which I consider like a trustworthy development pipeline, abstract interpretation can be used for training. So we can formalize the goals of safety uh, as a specification, and then have abstract interpretation be involved during training to train networks satisfying those specifications. And I will discuss how this can be done. Um, then it can also be used for testing, and I will tell you what testing mean in this context. And also like we have also developed methods for interpreting this large deep neural networks. Okay, so let's first look at testing. Uh, so in general, the DNN certification problem is an instance of testing, and I will tell you why. But let's first assume what is the DNN certification problem. Here, it's a classical thing. As in program analysis, you can see a neural network as a program, and then what you want is you are given a precondition phi, which gives you the set of inputs you are interested in, and then you have a property over the outputs, and you want to either find a counter example or you prove that the property holds. Right? Now, the problem in the DNN world compared to program verification is that we cannot specify all the inputs that we are interested in. For example, we cannot tell what are all the images of a car as a formal specification. If we could do that, we should probably not use deep learning. So what it becomes is like is local specifications. So the most common form of specifications that people verify for DNNs is I will take an image and I will apply some transformation on it, which should be semantic preserving. In this case, I can assume that I'm going to rotate the image between certain angles. And then I want to verify that all the images are classified as car. Notice this does not verify all the images of car in the world. It only verifies those images that can be obtained by rotating the original image. So in that sense, it is testing, because what you do is you take a bunch of images, usually from the test data, 10,000 images, and then you define some rotation specifications around it, and then you check how many of these images can you verify. Now, using how many you can verify, you can try to compare or quantify which neural networks you want to use. We, in general, for these kind of like text domains or vision domains, the global specifications which can verify all the inputs do not exist, although there is some ongoing work on that in that direction. Right? So certification for DNNs is a form of testing where you just test the network on some specifications. These specifications are very large in number. It will be a key point as I go into some other works, right? So you have to verify a lot of images, and then using that, you can get a metric to compare your networks. So analyzing DNNs with abstract interpretation is similar to how it's done for programs. I don't have to like explain in that detail. What you do is that you take the precondition and then you propagate this precondition using symbolic propagation. And at each layer, you compute an over approximation of all the outputs. And then if you can prove the property on the approximation, then it also holds on the original input. So why should we do that much research, right? What is different about these machine learning models that you do not see in classical program verification? Personally, I have worked on both, and from my point of view, the main differences lie in the fact that for deep neural networks, you have a larger number of nonlinear assignments. For programs, most programs, not all, you have fewer nonlinear assignments. So for classical program verification, usually you get away with not handling those nonlinear assignments that precisely. Common domains like polyhedra, octagon, they do not try to compute very precise transformers for nonlinear statements. Also for linear assignments, they are dense in the sense that on the right hand side, you have a larger number of variables. So if you have an affine layer in a neural network, you would have y is equal to x1 plus x2 plus x thousand, right? 1,000 variables. For programs, usually the assignments are sparse. You usually have x is equal to y plus z, x is equal to y minus 2, something like this, right? So these differences, because of these differences, for DNNs, if you want to verify anything meaningful, you need to make sure that you are able to handle these nonlinear assignments and linear assignments as precise as possible. Now, one thing that is maybe useful for DNNs is that we don't have loops for most DNNs. Programs usually have loops, so then you have to worry about winding for programs. For DNNs, usually the computations are finite, so you can unroll the whole DNNs even if it is a recurrent network. So popular domains that have been developed for programs do not work as well for DNNs. The reason being that in DNNs you have a lot of non-linearity, and these domains are not designed to be efficient for non-linearities, polyhedra, box, octagon. They are very common in program verification, but do not work so well for verification of DNNs. Another thing is that you have a lot of, as I mentioned, you have a lot of these dense linear assignments. So if you use something like octagon, it cannot capture uh, even like linear assignments that you see in DNNs precisely. This is one of the first thing we tried 5-6 years ago. It with the standard transformers did not do better than box. Zonotope turns out to be very well suited um, for neural network verification because it can handle linear assignments exactly, and it is quite scalable for it. And then you have to design some special ways to handle nonlinear assignments. The most common nonlinear assignments that you see in deep neural networks is ReLU activation. uh, it looks like a piecewise linear function. And what we have been doing, or people have been doing, and still there is some work going on last 5-6 years, is how to just for this ReLU activation, what is the best transformer, right? Um, so there have been a variety of like approximations, very tailor-made. We even had like Zonotope approximation. We had a new abstract domain which is quite tailored for DNNs, deep poly, which had specialized ReLU transformers. Right now, what you see is that these box transformers, of course, can be expressed by something like octagon, but deep poly or Zonotope, it cannot be expressed as an octagon transformer. So that tells you that there is a need for different domains for deep neural networks. Another thing I wanted to mention is that we have tried out some of these solutions for program verification. They do not work as well because some of the algorithms we designed are very much tailored for neural network analysis. Even if I just look at the distribution of polyhedra, the kind of polyhedra, I mean, all this Zonotope deep poly is a polyhedra domain, is very different from what we see in programs. Another distinction here was that the polyhedra or the shapes we get are bounded, while in program verification you get unboundedness, and then that also makes things different in the programs world. Now, I wanted to first discuss how can we use this abstract interpretation to give better insights into how the model work. So this is something I did while I was at VMware. So here in this case, this is a part of a product of VMware where they want to develop self-driving data centers. Basically, they train a controller with reinforcement learning to dynamically adjust the hardware resources on some data center. Now, issue here is that uh, they every week retrain the controller because they're worried that the distribution has shifted. So the issue for them is that once you have this kind of distribution shift, I train a new model. Is this model better than the previous one? So usually how they compared before the models was using just a standard reward. You check on some test inputs how much reward the new controller gets compared to the previous one, and then they deployed the one that was, if it was getting better reward, they will deploy it. So we said, oh, okay, but what about it could be the case that your new controller gets high reward, but it might be over optimizing for it, in the sense that it might not be stable, or it may not be satisfying some other properties. So we defined two metrics here, which are like robustness property. You want to check, if I change the state of the controller slightly, how much does the prediction change? And monotonicity is an important property here. You want to say that if my input features are increasing, then my output should also be decreasing. In terms of the result, what we saw was that the controllers that were getting very high reward were actually quite unstable. So it is the case that that the controller can over optimize for the reward, because it does not take into account the stability during training. So how this metric are computed is basically we take test inputs, and then we define preconditions around it, and then we check, maybe we get 10,000 preconditions, how many of those are uh, where the model is stable, and then we give a score to the model. And here the models that are the controllers that are getting the highest reward, which in this case is this this blue one. It's getting the lowest monotonicity score. I wanted to cover like more diverse problems. So for example, here we are looking into the job scheduling, where you have a bunch of jobs to schedule on some machine, and you want to decide which one you want to do next. This is a very important problem. Um, and then recently, like graph neural network based solutions have achieved significant performance gains over heuristic based algorithms. And then this was actually a major news a few years ago, 3-4 years ago. It was covered in media and so on, that with this deep learning based solutions, you are able to get better algorithms also. But again, the question is the performance enough? Because there are maybe other properties in this domain that a user may want. Fairness, locality are some of these examples. Now, for handcrafted heuristics, people usually do pen and paper proofs, and then they say, oh, this scheduler, let's say first in, first out, it's fair, and so on. It's very hard to say. It's very hard to do pen and paper proofs for GNNs. So in this work, we leveraged abstract interpretation to verify these graph neural networks. Now the main issue here is there are two details, because for graph for this kind of job schedulers, they are making uh, decisions over time space. So we want to have temporal properties that hold not over a single step but over multiple steps. That makes already DNN verification is very complicated, in the sense too many nonlinear behavior. Now you do it over multiple steps, it becomes much harder. Then in this domain, we have a output specification which has a lot of disjunctions. Further, graph neural networks can be unrolled, but when you do unrolling of these graph neural networks, you get more than 100 layers. So if you do abstract interpretation for this kind of problems, it becomes too imprecise. So here, to control this imprecision, we have a forward backward loop, where when we do the forward pass, then we intersect that with the post condition, and then we refine the output, the analysis output, and then have this operate in an iterative manner. Um, to handle disjunctions, we have concepts of node abstraction, which is also like iteratively refined. And then we have method for multi-step reasoning. We don't have to go into the details of this, but I wanted to give you like the kind of adaptation you need for handling this kind of real world problems. One property that we have looked into is strategy proofness. So here you have jobs. Jobs are represented as graphs. So here we have two jobs, and the two graphs with red and blue, the edges determine the dependency between the different sub jobs of a given job. And here, initially, what happens is that for each node in the job profile, you have a set of features which tells you, for example, how much duration this task will take, how many subtasks it has, and so on, so on. So the graph neural network takes the graph as well as the features of each node to make a final decision about which node should be scheduled next. That also satisfies the dependency. So in this case, let's suppose our graph neural network selects the node 4, P4 here. The probability for this is highest. Um, okay, so what we don't want is that if my first job wants to get its node 1 scheduled, to lie about its requirements. So now it says, oh, I'm not going to run in 100 seconds, I'm going to run in 1000 seconds. Because if it can do that, then all the users will be incentivized to lie about their resources, lie about their features, and that would actually make the whole pipeline inefficient. So here the specification means that if I have uh, uh, some features related to duration and I have some range for it, what I want is that my original prediction should not change. This is very different from robustness in the sense here you want the prediction to change, but not adversarially. What it means is that I don't want P1 and P3 to be scheduled, but P5 can be scheduled. That's fine. So the actual specification we verify is more complicated, uh, but I wanted to give you a details of like what we found is that in general, this Decima has some cases where it is not a strategy proof. We have done both single step and multi-step. Multi-step, we do 5 steps. And we have found some instances where it is not a strategy proof. So that's again calls for a need to actually maybe retrain this Decima to satisfy a strategy proofness property or increase the amount of time it is a strategy proof. Uh, Another thing that we have been looking into recently is we are not doing specifications defined over the network output, but we want to verify specifications related to the gradients, right? This is more diverse than just like the kind of verification people have been doing in the last few years. An example here would be computing the derivatives of the Black-Scholes solution, which is a very popular model in the finance domain. And we want to check how these derivatives uh, are affected by different parameters of this model, such as volatility, strike price, and so on. Uh, it requires analyzing an autodiff code, which is more, actually even more nonlinear than DNNs. To give you an example, uh, when you analyze the gradients, you have more diverse nonlinearity because of chain rule. Chain rule here takes the derivative with respect to a nonlinear function, and then it will also have multiplication, right? Product rule has multiplication and plus. For quotient rule also we have divisions, multiplication, and so on. So as I mentioned, for program verification in general, when you have division for polyhedra domain, usually because things are unbounded, you use interval transformer. You would take the interval for the denominator. But if we did something like that here, we will not be able to prove anything. So we have to actually design specialized abstract domains and specialized abstract transformers to handle these kind of computational patterns. Um, and autodiff computations can also be done in forward mode and reverse mode, depending upon uh, the program that you're analyzing, the DNN you're analyzing. Either mode can be fastest. So we want to also be able to compute these computations in both modes. We don't have to worry about it for this talk. Uh, so this is work that Jacob will present tomorrow. Tomorrow, which is in Uppsala, I think on the second day. Uh, what we did is we have a general method of synthesizing uh, abstract transformers for nonlinear patterns that I just showed you before. So in this case, I'm giving an example of the chain rule. So the leftmost is the actual function output gxy in some region that we find during analysis, and we want to compute sound linear bounds on that, because nonlinear bounds are usually very hard to compute and propagate. So here what we do is we do some linear regression to find some plane that bounds the original function from above and below. Now these bounds can be in the middle, these bounds can be imprecise. So you want to adjust these bounds so that you get soundness. So we have a specialized method to compute this sound bound that requires solving complex multivariate optimization function problems. In terms of results, if we do this kind of synthesis where we are synthesizing a single transformer for a bunch of statements as compared to if we applied standard abstract transformer for each nonlinear statement, we get much more precision. In this case, up to 4 times better than interval and 2.8 times better than Zonodope. In the paper, Jacob will also mention that we can also compute similar bounds on the sensitivity of neural ODE solvers for chemistry and climate. These are all new applications in the sense that people have been trying to compute this kind of sensitivity previously in the scientific computing domain, but mostly they do some kind of sampling which does not give you certified bounds, or at most what they do is they can analyze interval domain. We have also recently been looking into the relational verification of DNNs, which is very important uh, for verifying many important properties like monotonicity I mentioned, and also like there is a threat model adversarial attack, which requires an attacker to add the same perturbation to each input, right? So here you have a set of inputs x1, x2, and and you want to find a single perturbation that can be applied to both to cause high error. And the verification problem is, what is the worst case accuracy of the model when the same perturbation is applied to all the test inputs? Now, because the same perturbation is applied to all the inputs, the executions are correlated. So you have to reason about multiple executions at the same time to gain precision. So in this direction, we have we have Raven, which is a framework for relational verification, something that we are developing. So here, the main contribution that we have is concept of a difference DNN, which captures the difference between between the output of the network on two different inputs. And then we have a specialized abstraction called diff poly that can track the difference of the network on two different inputs through all the layers. And using that, we can actually get much more precision. And I will give you example here. So we want to compute how much is the network accurate when we do relational verification versus if we just verified each execution individually. So what you see is that once you do relational verification with Raven, you can prove much more here. For example, in the third figure, uh, you get much better bounds for this kind of verification. Now, this kind of attack like UAP, universal perturbation, which requires you to add the same perturbation for each input, is actually more realistic, because imagine if you have a self-driving car and you want to attack it. Does an attacker really know what input the network will be processing? Mostly not. So what you want in the actual practical scenarios is to create an attack that is input agnostic, that does not depend upon knowledge of the input. So this is what this UAP does. And in this case, if we assume this weaker attacker, we can actually get better bounds on the robustness of the network. This again is an instance of testing with verification, where you define set of inputs and then you verify how many of those can be verified, how many of the specifications can be verified with abstract interpretation. Another thing which I mentioned before was that even with all the developments we have done in the last 5 years, if we want to actually consider this kind of trustworthy pipeline, uh, the certifiers are inefficient because in this pipeline you have to train multiple networks. If the network is not uh, trustworthy, you have to train it again. You also have 10,000, 20,000 specifications. So if you have to run for each specification and each DNN, the network, the verifier from scratch, it's inefficient, right? So what we want is we want to develop incremental certification. Basically, if you verify a given network and you get a proof, you want to transfer this proof to verify a network that would be similar to the previous network. You can also do it across specifications. So if you have verified a specification, can I also verify a similar specification with the proof that I just generated? So we have done this for a class of certifiers. So when you have ReLU activation, you can actually do complete certification by using SMT solvers or mixed integer linear programming. But the more scalable versions are like incomplete certifiers, for which we also last year had a work, and we also are looking into probabilistic certification. That's not something I'm covering in this talk. But to give an idea is, Ivan, this was presented at PLDI this year. What it does, it uses the proof when verifying an original network to verify a new version of it that is similar to the previous one. So we consider complete certification. These complete certifications are usually based on branch and bound. So what this Ivan does, it tracks what branches or what decisions were used when verifying the original network, and then uses those decisions to speed up the certification of the approximated version. So you don't have to do verification from scratch. And if you do this, we have looked into different kinds of changes to the network based on quantization and pruning. It gives you more speed up. Important next direction is, can we actually train the network such that you can do incremental certification across different networks as well as across different specifications. Another important thing I wanted to mention here, which is coming from my previous experience developing all these libraries for numerical abstract domains, it's very hard to develop. It's like 30, 40,000 lines of code of very low level C code optimized, so on, so on. Even for like neural network verifiers, I have like Iran repository, and uh, there are bugs at a lot of places, and then fixing them and maintaining them is very complicated. So your algorithm can be correct, but then the implementation can be unsound, and there have been cases where unsoundness results have been reported, right? So what we want is, we want to make this abstract interpretation more democratic, in the sense that anybody should be able to write, especially for neural networks, is very important because things move very fast. So I should be able to design new abstract interpreters by not writing 20,000 lines of code. I want to make it easier to do it. So for in that direction, we are developing a new domain specific language for specifying abstract interpreters. So currently we are only focusing on neural network abstract interpreters, but we believe it can be extended in the future for also like classical polyhedra, octagon domain, and so on. So here, uh, uh, first we define the abstract shape. In this case, we are looking at something like deep poly, with which each neuron associates two polyhedral expressions and two upper and lower bound. So along with this abstract shape, you also say, what does it mean for that shape to be sound? So what condition do you need for your abstract shape to be sound? And that is given in this annotation in orange. And you also have polyhedral expressions as first order constructs, instead of like having them specified as like vectors or complex arrays, you just have a type for polyhedral expression, and then you can specify something like a deep poly analysis, which I implemented in 20,000 lines of code in basically 10 lines of code. So you have a special construct which mentions what is the transformer, and then you can specify different kind of transformers in a declarative manner. There is no pointer arithmetic, and for neural networks currently we do not have any kind of uh, we do not support loops. And when you have computations that require some kind of a traversal, because deep neural networks are kind of graphs, so you have graph algorithms in these domains. You can specify some invariant, and then we can actually check if this is a valid invariant. And then we have special constructs into how these transformers are combined. So what we want in the long term is we want to be having this DSL where people can specify their abstract interpreters in 10-20 lines of code. Then we should have a compiler that takes this code and generates optimized abstract interpreters. The thing that we support currently is we do bounded automated verification, which tells you whether your implementation is satisfying this over approximation property automatically. As I mentioned, sometimes you have to provide invariants for certain transformers, and that's something we also want to do in the future, how to synthesize this automatically. So in this case, I'm looking at a deep poly domain. We have a ReLU transformer, and we want to we want to like check whether it is satisfying the over approximation property. So we have operational semantics for this DSL that tells you what is its behavior on individual inputs, and then we have developed symbolic semantics which tells you what is its behavior of the code on a set of inputs and set of DNNs, right? And then uh, we have a way of executing this symbolic graph such that we can prove that anything that we can prove on this symbolic semantics also hones on the concrete semantics. So with this, we are able to give a feedback to developers whether their abstract interpretations are sound or not. So that in my opinion should reduce the bugs and increase the the time to develop these abstract interpreters. So what I want is that all of this technology that we have, all the research in the last 45 years should be accessible to common people. They should be developing this. They should also be using these tools without a lot of overhead. Uh, Training, I will just briefly go through it. I guess we are running out of time. So training, the point is that many of these abstract interpreters, a very important thing for deep neural networks, are differentiable. So it's kind of a wacky idea. So imagine you want you have a precondition phi and you want to check the post condition phi psi holds or not. So you can do your usual abstract interpretation to get an output. Now what you want is you want to use the feedback from this abstract interpreter to adjust the model weights such that the property is proved with the abstract interpreter, right? So what you do is you involve an abstract interpreter. The idea is different from counter example guided learning, because in my opinion that gives you a more indirect way of modifying the weight by giving you a counter example. It does not give you the direction in which the model weight should be updated. So here the idea is wacky. So what you do is you take the abstract interpreter, all the computations in the abstract interpreter are differentiable. Then when you get the output, on that output, you define a differentiable loss such that when the loss is zero, the property holds on the neural network, right? For different properties, different formulations exist, robustness, fairness, so on. Then the important key here is that you differentiate directly. You compute the loss and then you differentiate it directly through the verifier code, right? So So with this, you get the gradients that are with respect to the verifier. It's not indirect like a counter example. and then you are able to adjust the weights in the direction of where your abstract interpreter will be able to prove the property. So that's the feedback. You find a point where the loss is highest, and then you differentiate directly through the verifier code. You do not differentiate through the DNN, you differentiate through the DNN verifier. And in terms of this, as I mentioned in the beginning, we had looked into this case where you can rotate or scale or do all kinds of geometric transformations to a cat, and we want to prove whether the network is still robust in the sense that the prediction does not change when I have added those perturbations. Uh, the classical is like you do some kind of LP perturbations noise, and then you want to check whether the prediction does not change. So geometric transformations are very meaningful, but there has not been much work on verifying them or even training the networks such that these can be verified. So I will briefly mention that we have this framework published at ICLR where we apply that idea. And usually in the machine learning community, people talk about like robustness accuracy trade-off, which means that if you train the network to be robust, the accuracy decreases. And then a lot of people say that, oh, this is not practical because we are losing a lot of accuracy, so we should not do any of this. Well, there's even theorems about that this cannot be done, but I do believe that this is more a property of your specification that you are trying to verify, and also the data set that you are handling. So in this case, we have a data set from NVIDIA, which is for self-driving cars. And and here what we see is that once we train the network to be robust with abstract interpretation, not only is MAE is mean absolute error, it reduces compared to just standard training, but also the certified means absolute error, which again means you take all the rotated images and then you see how much does the output vary. That also reduces, right? So in many cases, I would say it is possible to get both safety and accuracy at the same time. Uh, the last thing I wanted to talk about was interpretability. So here we are looking into proof interpretation. So imagine like um, when we do proofs for programs, you find some invariant either automatically or by provided by human. These invariants are usually interpretable or understandable to the developers of the code, right? So in this case for Fibonacci, I have some invariant that if I know what this computation is doing, I can see, yeah, it makes sense. So we have been verifying all these deep neural networks for the last 4 or 5 years, and we compute proofs, or we say, oh, this network is robust. The question is the proof meaningful, right? So you can prove a network to be robust under some kind of perturbation, but then you want to check, hey, is the proof capturing something that is human understandable or meaningful? In my opinion, if the network is going to be trustworthy, then it not need only be proved robust, but it should have robust interpretation that we should be able to trust. Yeah, it's getting verified, and this verification is based on some properties that we can understand. So the question we ask here is, are the features learned by the verified neural networks is actually like human meaningful? And the question is that the main problem here is that how do we interpret the neural network on these preconditions with respect to the proofs? In the interest of time, because we don't have much time, we have this algorithm that can interpret these proofs. Basically what it does, it finds the neurons which are the most important for the proof, and then computes the saliency map of those features. I wanted to highlight an important observations from here. So this is MNIST data set, and all these networks, there are 4 networks here. One is trained with standard training. PGD is kind of adversarial training where you train the network such that you cannot create adversarial examples. Crown IVP is the certified training I talked about, which involves abstract interpreter, and Colt is something that combines something in between PGD and Crown IVP. So we have 4 networks, and all those 4 networks, we have verified robustness. And now we check which neurons are the most important for the proof, right? What you see here is that these networks, even if they are proved to be robust, the proof features or the proof relies on very different information. So if you look at the standardly trained network, um, it relies a lot on the background noise, right? Basically this red part, which is not even part of the object. So this is surprising, like you are able to prove the property, but it still is relying on a lot of spurious feature, which also tells you that maybe just verifying is not enough in this context. The Crown IVP is other extreme, so it is it regularizes a lot for the network to be robust. So in this case, it removes a lot of features from the input and also something that belongs to the actual digit that you are trying to identify, right? So something like PGD and Colt from our experiments seem to generate more interpretable proof. The question would be next is how can we integrate, or if we want to integrate these kind of interpretation in the training pipeline to get networks that are not only robust, but their proof also relies on robust features. Okay, so with that, I would like to finish, and thanks for your attention, and I will leave you with the 6 most important slides from this talk. Thank you.
Well, thank you very much for this fascinating talk. Do we have questions? Either here or online. Any questions? Well, people think there are questions. I mean, I can ask one at least. So you tried the traditional domains, and they didn't work because of the characteristics of the the nonlinearities and so on. So you came up with these domains, the zonotype and the deep poly, and so on. Yes. So my question is, and then you said, okay, so these are new domains, and then I try them for program analysis that are not so useful. So I thought that was very interesting. So have you learned anything else that can help in traditional program analysis? I mean, of course, the analysis of networks is fascinating, but can we get from this work some inspiration or something we can do better in traditional programs?
Yeah, so that's something I am very much interested in kind of like synergy between the two, right? So one thing that I'm really interested in, and I think you can still see the slides. So for example, right, like here, what we have done here is that we have found we have a general method for synthesizing new transformers for particular computational patterns, right? And the reason why we did it is because if we usually in program analysis world, you design abstract transformers for each statement, and you compose these transformers for assignments, conditional, and so on. Now, sometimes these transformers are not exact, so imprecision can accumulate over computations. So the question is, here for let's say autodiff, we have identified this computational pattern that appear very often, and then we have a general method to compute a single transformer for a group of statements. So a single transformer for a group of statements is going to be more precise than if you did transformers for that were imprecise for individual statements. So can we do that same kind of precise synthesis procedure for a group of statements for polyhedra domain in programs, right? So that's something we want to look into, is how to generalize this kind of procedure for the patterns that we see in programs, and what are these important patterns. The important thing that I really these days am interested in is, see, for programs, usually we have loops, and then we try to do abstract interpretation, and after some iterations, we do widening. Widening takes you and takes us anywhere in the loop, right? And what I want to do is there any connection between kind of the network training that I also mentioned and this widening that we are, let me show you here, of the loop that we do. So what I want is I want to do the fixed point computations, right? That we do in traditional abstract interpretation, guided by some kind of loss function. So this loss function should tell me how far am I from the fixed point, or at least give some quantification of how much I can improve before I should do widening and so on. I believe that for certain kind of programs, this could be done. Currently, we are able to do it for neural networks, which are also like programs, differentiable programs. But is there a more expressive class of programs where we can have this kind of widening, which is guided by some kind of differentiable loss function that gets me a more precise invariant than possible with just widening, which does not take into account the property of the lattice or the property of the program I'm analyzing.
Right, thanks, great. Any other questions? People too fascinated if I... I actually have another one. I mean, is there a connection? This goes in completely the opposite direction. I mean, it's more towards the user than towards the analyzer. Is there a connection between the proofs, you know, being able to make the proofs more understandable by humans and so on, and therefore and explainability? I mean, the general, obviously that's what you want to get to, no? So can we use abstract interpretation and so on to generate good explanations that humans can understand of why their neural network came to the conclusion?
Yeah. Yeah, so for explanation in general, there is a trade-off between simplicity and faithfulness, right? So simplicity means that you can understand it, and faithfulness means that the explanation should actually describe the behavior of the model. Now, there are a lot of like this explanation method in the ML literature, like Lime, SHAP, and so on. These generate simple explanations, but they are not very faithful because imagine if I'm going beyond Lime and SHAP, if I'm just looking at the vanilla gradient maps, right? The gradient map will just plot the function output on one input, right? So what you do is that you take an input and compute the derivative of the function output with respect to all the inputs on a single like example. Now developers, what they do is that, oh, I looked at this interpretation on single inputs and it looks good, so let me deploy it, right? But the problem is that uh, it can be correct on a single input, but if you take a larger region around that input, it might not be it might not be understandable. So for the proof, even if we are going for proof interpretation, if we were to just look at the behavior of these models on individual inputs, you would say that okay, this looks interpretable, human interpretable. So with abstract interpretation, you can compute abstract saliency maps or robust saliency map. This is also something we have done previously. I did not cover in this class, in this task, in this talk. Sorry. So there, what you do is you compute not single gradients for a given input, but you compute abstract gradients, which tells you what is the saliency map within a region. And once you get that, you have a more global understanding of how whether you can trust the model's prediction or not. Now, these things can also be generalized for other kinds of explanations. I think there's also a scope to generate models that actually produce proofs that are human interpretable, but we are not there yet.
Thanks very much. So, any question in the meantime? Otherwise, I think we've completed the hour with the delay, the initial delay and everything. So thanks very much for this great talk. And anyway, bye for now. So I think we should thank this people. I don't know if you heard it, but it's a big round of applause here. All right.
Thank you.
So with this, we go to the next part. We'll try to accelerate a bit. So we come to the second part of this session, which is very, very important. Is the Radio Cousteau Award, the Radio Cousteau Young Research Best Paper Award. The award, as you know, was instated in memory of Radia Cousteau, co-inventor of abstract interpretation with Patrick, and with many other fundamental contributions to static analysis, as well as being one of the main promoters and the main and the founders, and one of the founders and organizers of the SAS series of conferences. The award is funded by the ENS Foundation, and we are at the 10th edition, and it's time to announce the winners, but Jose is the one that was going to announce the winners, and
So the winners of the Radio Cousteau Young Researcher Best Paper are Jocelyn Diet, Félix Ritou, and Xavier Riva for the paper A Product of Shape and Sequence Abstractions.
Okay, great. And then, is there a way to take a picture for posterity? For somebody like so come over here. We'll do a picture. Take a picture of them first, and then we can take a picture of them first. Yeah.
Hopefully the phone camera is good enough. Thanks everyone. Okay, and then chairs.
Also, with the chairs. Congratulations, big congratulations, buddy. It has a cash award also, I should say. Okay. And with this, we start with the PC chairs report.
You should see the image there.
Okay. We have it. So, okay, good. So you can see the PC here. It's working. You cannot see the PC here. It's there, but it's not on the projector. We can see it there, so you're getting the signal. Okay. I don't think it's your problem because you can see it there, so there's some connection. All right, so I can do from here. Okay. So here you have the image. You do have the image of all the program committee members. Some, well, not of some, the ones that provided pictures, I mean. We formed the PC at the end of March. About half of the PC was from the 2022 PC, and the other half was all new people. So that to have a balance between continuity and renewal. We had 4 women and 21 men, which is not very good, but it, you know, you see there the statistics from other years, and you know, it's not easy, but I mean, at least we did something. And then for countries and regions, I think it's, you know, I think it's pretty balanced, or we try to balance it. 9 from the US, 3 from China, 2 from Australia, 1 from Taiwan, from the more Asian region, and then from Europe, 3 from France, 3 from Italy, 1 from the UK, 1 from Germany. We also had an artifact track. Marc Chevalier, who couldn't make it to the conference, but he did a fantastic job, you know, forming the Artifact Evaluation Committee in April, and he put together a fantastic set of people, which did a really good job. We set up social media presence as in 2022, and Louis Rustenholz, who's the publicity chair over there. Louis, raise your hand. That he has been, you know, has been sending all the messages there, and is sending messages for each talk and so on to keep the. So you have here, that's Louis' name. There you have the pointers and so on. We had more than 250 followers. First message was sent out on March 17th. We got 1,800 views, 13 retweets, 19 likes. We sent reminders before the deadline. We announced the deadline extension also through the social media, and during the talks we're giving, you know, we're putting up photos and so on. One thing to consider is maybe if we want to use alternative platforms, platforms other than Twitter, X, you know, for next year, Mastodon, for example. So that's something we can discuss. Paper submissions. This is your part, no? Yeah. Okay.
I can. Yeah. I will explain briefly some statistics and numbers about the submissions and all of those data. So the paper deadline was on 24th of April. We had our first paper on the 13th of April. Indeed, we had another one even before, but it was a desk to reject some paper that has absolutely nothing to do with SAS. The deadline was extended until the 1st of May. We can see from the data that most of the papers came the day of the deadline, and then we extended, and this gave us like 4 additional papers from. Actually, it was a good idea. We think because one of those papers was actually accepted, so it gave the possibility to have one more good paper. This year we had 40 full submitted papers, 38 regular papers, and 2 need papers. More or less, this is similar to what we had in previous editions. In past year it was 43. The year before 40, 34, 50, 37. So we are not much better than in other cases, in other years, but we're not worse. We're more or less the same. Regarding the number of authors per paper and papers per author, the trend is very similar to what we saw in the past edition. Most of the authors send 1 paper, and most of the papers are written by 2 authors. Regarding the artifact evaluation, we got 12 artifact submissions. This is a similar number to what we had in the past editions, maybe a bit lower. As you know, papers have some, after the artifact evaluation, the accepted papers may have some stamp, some budget that can be validated, extensible, or available. Where validated is just the minimum thing is that the results, the experimental results, could be reproduced by the Artifact Evaluation Committee. 3 papers got this badge. Additionally, the papers could also get extensible badge, meaning that it is both validated and extensible, meaning that the the source code was available and that it seems for the artifact evaluation committee that the code could be reused for other things. So 7 papers got this badge, and some other papers, I don't have here the numbers, but also I think most of them were archived on the Zenodo platform. That is just a way to preserve this for the posterity for the years. One artifact was validated, but the paper was unfortunately rejected, and one other artifact was rejected and the paper too. So about the review process, as you know, SAS follows a double-blind 2-round review process where the PC members and the 23 external reviewers produce reviews for the papers, at least 3 reviews, in most of the cases 4 first-round reviews per paper. The reviews were due for June 9, and authors could respond to reviews in this period, a few days later. The response from the authors were taken seriously and they were followed by PC discussions, where most of the discussions happened on EC Chair. We tried to solve all the discussions there, and the tentative decisions were we got tentative decisions for all except for 7 papers, and we solved these pending things during the virtual PC meeting on June 26. Most of the all of the pending papers had PC members from all the time zones, so it was a bit difficult, but we managed to do it. And finally we reached a consensus. We got 5 shepherding, and on June 29, the authors were notified, and finally we got the final version on the 3rd of August. And regarding some statistics about the submitted and accepted papers by country, as well as the acceptance rate, we can see in this graph. So overall, we had 20 papers. 20 papers were accepted, 19 regular papers, and 1 neat paper. Regarding the number of contributions, this follows a similar trend in the past years. Most of the contributions comes from China, US, France, Germany, and Italy. The acceptance rate follows like an inverse relation. So Italy get the most acceptance rate, then Germany, France, US, and China. And that's what we have. Okay, and here, maybe you continue here.
Sure. So we would like to thank our sponsors for the generous support, Google and the ENS Foundation, also Meta, Absinthe, Amazon, Springer, and the MDA Software Institute contributed in several ways. And we also want to thank Springer for hopefully eventually publishing these proceedings. All right. And last thing is the announcing. So do you want to come over? Yeah, you. Yeah. So he doesn't know, but it doesn't matter, no. So the announcement is that SAS 2024 will be organized by Roberto. He does know, he does know. I know. So Roberto, if you want to say something.
Okay, yeah, it will be in Pasadena, I think, yeah, so California. And because I'm now not that far away from there, so I'm in charge of that. I'm looking for a co-chair that I still need to find. I try to do my best, disappearing. Well, I need to find a good balance between men and women, so I need to look on that side. And well, that's it. I took all the images from your work because you made a great work for this SAS, so I hope to do the same for the next. Thank you.
All right. Thanks. Thank you, thank you. So many thanks to Roberto for accepting, and with this we close this business meeting. And anyway, let's go and enjoy the rest of the evening. Thank you.